has been doing for decades. But these gave two different answers. One said the cycle was going to be bigger than average. One said it was going to be smaller than average. And so how do these things do? In terms of the predicted max is here with the uncertainty quantification. As I said, cycle 21, they didn't do a consensus prediction, but pretty much all of them were wrong within these stated uncertainties. So if you look at the uncertainties given here, the actual observed max lies outside of the uncertainties, with the exception of one. The weaker of the two predictions that were released for cycle 24 did fall within the stated uncertainties. So the panels have been very useful from a research perspective, but they are not enough to rely on from an operational perspective. You need to update the predictions. If you want to know what the weather is going to be like tomorrow, you don't look at the forecast made last week. You want to include assimilate all the data up to now to make a good forecast. So that's what we did. So this is the new product, and we have a new website at Space Weather Prediction Center. It's called the Space Weather Prediction Testbed. So it's a testbed website. This is for new experimental products, but it's basically a pipeline for research to operations. And so this is the new product. It's predicting a max between 137 to 166. The mean of that is about 152. And it's put out for the sunspot number and the F10.7. And so how this is obtained, it's quite simple. We wanted to remain faithful to the 2019 prediction and the panel, but we wanted to update it with new data. So we used the same functional form. This is based on the average cycle profile from David Hathaway and company. And it's a 4-parameter function, nonlinear function. The A here is related to the amplitude, the T related to the start time. B is related to the rise time, and it works so built into the function is the known relationship that large cycles tend to rise faster. So that's built into the relationship. And then we have a skewness parameter, sort of C here. So you set sort of B and C, and you fit for the amplitude and the T0. Oh, and I should say the uncertainties here are based on making that same fit to previous cycles, 6 to 24, at the same month in each cycle. So that's how we, let's see, I don't know, can you play this movie? I don't know how to do it with the remote. This is how the prediction has changed since about 2 years into the cycle. So here's a way of looking at the same thing. This is the amplitude and the date of max in terms of the range. This is when we made the prediction public in October of 2023. So it is updated every month as the new data comes in, but it hasn't changed much since the year or so since it became public. And so we put out this product, and the customers said that this is great, we love it, it's a lot better than what you had, but what about cycle 26? Because the satellite people say, we're planning missions a decade in advance. So we wanted to approach this in a little different way. Rather than make a prediction for the amplitude of cycle 26, which is what everybody does, what is it you really want to know from an operational perspective? You want to know what the probability that the sunspot number will have a value of S at some time t in the future. And you can break that into the probability of the start time, the probability of an amplitude given the start time, and if you know the start time, you know the amplitude, what's the probability that you'll have a sunspot number of S? So we know this probability of start time is just the period of cycle 25, right? And then 26 is going to start at the end of cycle 25 by definition. And if we know the start time, there's a known relationship between the period of cycle n and the amplitude of cycle n plus 1. So we turn this into a probability density function, into a regression fit with a Gaussian cross-section. And then let's see, I know the amplitude, I know the start time. What's the residual? Well, I can go back to the previous cycles and say, the last cycle I knew the amplitude and I know the start time, so how well does this function do in fitting what actually happened? And so you can compute a bunch of residuals from those past cycles, and so you can come up with a point cloud that looks something like this, and then you can do a kernel density estimation based on that point cloud. And this is sort of what you get. This is sort of a 50% confidence interval. This is a 95% confidence interval. And this is just the mean cycle, which is the usual default thing that people say what the next cycle is. This blue line would be the mean, but this is sort of more informative. And I'll stop there with the summary. I think, yeah. So the summary is that this is a very simple method. But I would argue that any more sophisticated method based on dynamo models or surface flux transport or anything you want, it has to be at least as useful as this. So this is kind of a minimum bar. And it could be used as a first step in a Bayesian chain. This could be like your first guess. And then if you pull in other observations like a precursor, then you can modify that and get a posterior distribution based on new information. And then in terms of cycle 26, this is a preliminary guidance before the cycle, preliminary guidance for space weather customers. We will probably have another panel for cycle 26, but this gives satellite people something to go on until that happens. So I'll stop there. Thanks.
Thank you, Mike. Anyone for questions, please?
So I have not been a big fan of the way NOAA NASA panel went about this forecast. I don't know how you get 50 people together in a room and reach a consensus. So I'm glad that you have evolved this new technique. But having said that, this technique relies on data from the early part of the cycle. You cannot use this for a prediction at sitting at minimum, whereas your customers would like to have that knowledge 10 years in advance. So perhaps you may want to fall back on the physics-based models and update them with this empirical technique as we go forward. Maybe that amalgamation of these two methods could be a better way moving forward.
Yeah, absolutely, I agree. And I think physics, at the very least, for example, surface flux transport, as you know, SFT models can give you, improve the lead time on precursor models. So they can give you an estimate for what the minimum dipole strength is. And that, so that's what I mean by this Bayesian chain, that you can start with this as initial guess, and you can pull in other information as it becomes available. As you can start with the SFT estimate of the dipole moment, but then when you actually get to the minimum of that cycle, then you can update it with other information. So this isn't the last in the story, but and another thing I think the physics-based models can help with is ensemble methods for uncertainty quantification. So,
thank you very much. Okay, a quick question, Alex.
All right, quick question. So there are already indications from Helios homology about cycle 26. So I don't know if you plan to include that as, you can determine the starting time of cycle 26 from this, I think.
For the timing or the amplitude?
For the timing, for the timing.
Yeah. And that's another thing. I would like to update this, as I said, with more information. And so there's more work to be done here, but this is a start.
Okay. In principle, we have -5 minutes between this session and the next one, but we have already used this time up. But if your question is very quick.
I'm just curious if in this method that is based on probability, you discriminate between even and odd cycles, if you have tried to do
Not
that.
currently,
No?
but that's
It might
another
be.
thing that could be pulled
Yeah.
in. I think, I have high hopes that this is the way to really pull in all the information that we have, that you start with one thing and then you, like data assimilation in meteorology, I mean, you have so many different types of observations.
Yeah.
And yeah, this is a framework that you can pull them all in, but it hasn't gotten to that stage yet, but I hope that's the direction that it'll go.
Okay, thank you.
You said, this was a quick question indeed. Okay, thank you, Mark. And this was session 2, and now we, I think, move on to session 3. That's the heliospheric impact. And the first speaker is Marek Stawicki. Sorry if I pronounce your name wrongly. I give you 5 minutes warning of your total time. That also includes the question time, okay?
Hello, my name is Marek Stawicki. I'm working at the Space Research Center Polish Academy of Sciences. And today I wanted to present you our work with ULA on the temperature profiles of the coronal streamers. The title is a bit misleading because the full cycle now... Oh, okay. Because full cycle in this case is the full decay phase of the last cycle and the rising phase of current cycle. Coronal streamers, there are very prominent, long-lasting features of the solar corona. They have closed loop lines filled with dense plasma, mostly bright plasma, below the cusp, which is somewhere at the height of 2 or 3 solar radii. And then there is a stalk, which also is prominently seen with a dense solar wind. In case of streamers, regular helmet streamers, there are above the photospheric polarity inversion line, and which is then propagated to the heliospheric current sheet. In the case of pseudo streamers, which look more or less the same, we don't have it. We don't have in this case a polarity inversion line. When we look to the streamers edge on, in case of helmet streamers, these proper streamers, we can see at the bottom of the streamer, in the base of the streamer, a cavity. In case of pseudo streamers, the base of the streamer is much more magnetically complex. In such a case, in this simple case as it's shown on this cartoon, we would see two cavities at the bottom, and above them the cusp. So as we know, coronal streamers or the corona, which is seen during the eclipses, mostly in the corona we'll see the coronal streamers, is differ during the minimum and maximum of the cycle. This has some implication because coronal streamers are the main driver or main source of the slow solar wind. And in fact, solar wind is dominated by the fast or slower wind in different ratios during the solar cycle. In this case, solar cycle 23. We have more fast wind when we are near the minimum, and slower wind start to dominate when we are near the maximum. Of course, those are measurements near from the ecliptic plane, so near the solar equator. How it looks like in the other places, we still don't know. There are some clues that also temperature of the coronal streamers are different during the solar cycle. For example, temperature of the slow solar wind differs depending on if we are in the maximum of the solar cycle or the minimum of the solar cycle. Here we have the black points is the temperature based on the measurements of the oxygen measurements of the ionizations of the oxygen, and the blue line is the just sunspot number, which indicates the position in the cycle. Also, Ulla in her paper shown that there is indication that the streamers and the cavities, the temperature differs during the cycle. But she calculated. She was focusing on the cavities. That's why she calculated the temperatures of the streamers at the same height as the center of the cavity. That's why the temperatures of the streamers are measured on the different heights, depending on the height of the cavity, and this could affect the data. That's why we decided with Ulla to check the hypothesis that temperature of coronal streamers it depends on the phase of the solar cycle. We selected more than 250 streamers and pseudo streamers from 2011 to 2023. How they are spread in time is shown here in the case of streamers and here in the case of pseudo streamers. Those points represent the measurements, and of course this line is the average sunspot number, which indicates its position in the cycle. This number of streamers means that we have more or less 2 streamers each month. We took data from IAA. We averaged 8 frames in order to have a better signal-to-noise ratio. Streamers are bright, but not too bright in the case of the IAA observations. We also deconvolved the images. We noticed that the signal-to-noise is improved when we are higher in the corona, which is shown here. The red one are the uncertainties in the temperature when we do not deconvolve the data, and the blue one when we do the convolution, which improves the data, especially in the higher heights in the corona. Then we drew such paths along the streamer, 8 of such paths, mostly in the both sides, so 4 in the one side and the 4 in the other side. Sometimes where there are some other features shown in the frames which obstruct the streamer, we just took from the one side, but in the most cases it was taken from the two sides, and then we calculated the DEMs and average temperatures along those paths. Such profiles look like that. This is the average profile from these from these 8 paths for the one of the streamers. In this case, we have, of course, pseudo streamer, which these 2 cavities prominently seen here. But the same procedure was done for the streamers. This profile is consistent with the profiles which were measured for the streamers sound during the eclipses. So this is in the full agreement with the previous measurements. So how the profiles differ during the cycle? Here I just show for the comparison few years from the decaying phase of the last cycle. So we have 2015, 16, 17, and 18. In all cases, we have also streamers which were recorded in the year 2019, so during the minimum of the solar cycle. And we can see how the profiles are changing during that time. So here we have all of the paths which are measurement for the different streamers observed in that year, and the thicker lines are just lines which are overlaying the maximum and minimum of in such cycle. It is clearly seen that we have different mean temperatures of the streamers during maximum or more active sun than the more calm sun. How does it look on the graph when we include all the data we have? It is shown here for the streamers and pseudo-streamers, and the top we have just sunspot number, just to show how the cycle was changing. And on the bottom we have average or temperature ranges. In fact, those error bars represented the temperature ranges of the streamers and the height of 1.2 solar radii. So this is the height when the profile of the streamers starting to be flattened, more or less. And we can see some small dependence on the cycle. So we have rather hotter streamers when we are near the maximum and the cooler one where we are near the minimum. The same pattern is repeated for the pseudo-streamers. As we can see here, also temperature of the streamers is slightly lower, about 0.2 megakelvins lower than the temperature of the pseudo-streamers. The profiles are very similar, just pseudo-streamers are slightly shifted in the temperature, the higher temperatures than the streamers, and sometimes they are a little bit steeper, the profiles are a little bit steeper than the pseudo-streamers. Okay, I'm done, so I will just leave the summary slides. Thank you.
Thank you. If you want to have questions, then it's good to have at least 1 minute. Okay, anyone for questions? Sarah?
Really nice work, Marek. I had a question. Have you looked at the heights of the streamers? Because, you know, like at solar minimum, they tend to be taller than at solar maxima, and how that might factor into all this?
I don't know how to do it with this data. I can only look for the height of the cavity, for example. And yeah, maybe I didn't check it. Unfortunately, I didn't check it. I checked if there is a dependence on the latitude of the streamers, because it also can differ during the cycle, but the latitudes are spread more or less in the uniform way. So it shouldn't affect the data.
Thank you. I think we have to move on. Thank you very much, Marek. Okay, and the last speaker before the lunch is Ton Hassler.
Yeah, sounds great. Thanks. Okay, thank you, everybody. We're going to shift gears a little bit. We're going to go back maybe a little bit closer to the theme of Mark's talk a couple of talks ago. in the term of space weather prediction and asset protection, or in the sense of the theoretical or research aspects of space weather prediction. Let's see, the Curiosity rover on Mars actually has a heliophysics instrument on board. It's called RAD, the Radiation Assessment Detector. So this is a Mars mission, but it has a heliophysics energetic particle detector. It measures charged particles from protons all the way up to iron, from a few MeV per nucleon up to a few hundred MeV per nucleon. And it also measures neutral particles, neutrons, and gamma rays. And so Curiosity has been on Mars for 12 years now, over a solar cycle, and we've been monitoring and measuring the solar cycle and the energetic particle radiation on the surface of Mars for the last 12 years. I think one of the things that's been a great, exciting part of the program for heliophysics over the last few years is this building of this Heliophysics Systems Observatory that people like to call it. It's basically NASA and its partners have spacecraft all over the solar system. And so now anytime there's an event, a solar particle event, or any type of solar activity, we're observing it from multiple perspectives and aspects. And so RAD is a part of that here on Mars, on the surface of Mars. There's also the MAVEN spacecraft, which is in orbit around Mars. So the energetic particle radiation that hits Mars is very similar to what we see on Earth. We have galactic cosmic rays, and we have solar energetic particles, except Mars doesn't have a global magnetic field like Earth does, so it doesn't have its protective layer. So we actually have space weather hitting the surface. We have direct effects of energetic particle events actually hitting the surface of Mars. Also because the atmosphere is only about 1% of that of the Earth. So galactic cosmic rays vary slowly over the solar cycle. Mark talked about the difficulty of predicting the solar cycle. I'll talk about that a little bit more coming up. And then there's the solar energetic particle events, CMEs, storms, like we had back in May, much harder to predict, and they can happen really kind of at any time. So this is a kind of a summary of what we've seen on Mars. Energetic particle, let's see, the dose rate that we see on the surface of Mars is sort of inversely related to the solar cycle. Galactic cosmic rays have a minimum at solar maximum and the inverse. So we actually see our largest, the contribution you can see in the plot on the top. So this is a little bit of a complex plot, but the primary contribution to RAD's dose rate in a general time frame is galactic cosmic rays. And so this was solar maximum when we landed on Mars in 2012. And as we increase, as we go into solar minimum, our galactic cosmic ray flux increases, and then now we're coming back into solar maximum and our GCR flux is decreasing. These spikes are solar particle events, and I don't show the one from this May. I'll talk about that in a moment. Some of these were quite large, like GLEs on Earth. There's also Forbush decreases, which would be scenarios where there's a CME, which actually provides shielding from these really high energy galactic cosmic rays, but the actual energetic particle event is a soft event as opposed to a hard event, meaning that it doesn't have very high energy radiation that actually makes it to the surface. So we actually see shielding from those events, and you can see those little dips right here. So one of the things that's interesting about Mars, it's an asset which is not in the Sun-Earth line. So it's actually appropriate. There was the session last week on missions and science from off the Sun-Earth line. And so, so it's like one of the stereo spacecraft. Think of it as an asset that's moving around, but at a different, like stereo, it's always at a different longitude, heliospheric longitude compared to where Earth is. So in 2017, right in the peak of solar minimum, we had a large event, which we saw here at Earth. It was a GLE number 72, so it was a ground level event seen at Earth. And we also saw it here at Mars, about 170 degrees in longitude, all the way around from the far side. And at the time, it was also the largest event that we'd seen on Mars. So here was a scenario where you're on the opposite side of the sun, and we see basically the same solar particle event. This happened again in October of 2021, GLE number 73. Earth is here, and Mars is a little bit even further around, almost 170. That's about 175 degrees, I guess, in longitude around. Again, a large event. It was a large X-class flare seen on Earth, but not at Mars. But then a year later, there was an event seen at Mars, a very large event, February 16th, 2022, and we were only about 100 degrees away from Earth, and we didn't see this at Earth at all. So the reason I show these different plots is it's very hard to predict, whether it's based on cross-scale diffusion or what it is, the interactions of a coronal mass ejection, a solar particle event with the ambient solar wind, or the ambient structures in the solar wind as they propagate out. And so I think a really good example of that is this May event that everybody was all excited about. How many in the room saw the aurora in May? We actually were able to see it from our back porch in Boulder, Colorado, and it was spectacular. I don't know how, I guess I got it confused, but I had a slide which showed some beautiful pictures from that aurora. But actually, there was an aurora going on right now in North America. So, if you have friends or family or not North America necessarily, but the Northern Hemisphere, we're not going to see it here. But what's interesting is in this set of storms, there was a single active region which was acting up, and it started around May 10th or so, and it went for about 2 weeks. Well, it's been going on for a couple of months now, since May 10th. It's still been active, but it was affecting Earth starting around May 10th, and it went for about 2 weeks. And we started to, these are Mars data, but right around May 10th, we started to see the aurora. I think that was when the biggest aurora was on May 10th over here. Around May 14th, we started to see a little bit of the effects on Mars. And we saw one large event here and then one large event here, but they were soft events, as I mentioned earlier. They were large in flux, but they were soft in terms of energy, low enough energy. So the CME provided shielding in the heliosphere from the galactic cosmic rays, because what we're seeing here is basically GCR flux. But it didn't, the actual event itself didn't make it to the surface. And so what's interesting is the MAVEN spacecraft, which is in orbit around Mars, saw this event as enhancements in their lower energy solar energetic particles. And so the combination of these two, we can see, okay, this is a very large event seen at Mars, but it was a very soft event because it didn't make it to the surface. And then on the 20th, boom, we saw the largest event that we've seen since landing on Mars in 2012. In fact, this May 20th event was probably the largest event that's happened in the last 25 years. Having said that, there's a caveat. That's the last measurable event. We have to have assets to be able to measure one. But what's quite impressive is this is 8 times higher than we'd seen before. This is where the number came from. Someone quoted last week from one of my press releases last week that we had it's the equivalent of 30 chest rays on the surface of Mars. So if we're sending astronauts to Mars or if we're sending astronauts into space, we have to protect against these types of events. And these are a lot harder to predict than the general solar cycle. So this is looking at those data. A month later, the active region rotated around. There were some more events. There was a lot of news and excitement, but there wasn't any really high energy event that we saw on the surface. There were a lot of these Forbush decreases, which basically then just provided shielding. So, you can look at the different, another way to look at these particle events is you plot fluence versus energy. So when I talk about a hard event, it's high on the energy scale, and if it's a large fluence, it would be high on the fluence scale too. A Carrington event, the most damaging type events would be, high fluence and high energy. We don't get those very often. This one, so each one can be characterized by a different curve. So how do these events compare with these historically large Carrington events? Well, I think the events that we saw in May, people are still analyzing the data, but they really weren't Carrington events. They were exciting because they generated a lot of aurora. It got a lot of press. It made the public aware of this type of space weather activity, but they weren't Carrington level events. We still may see those. We're early in the solar cycle. I'm going to skip that slide but the prospects for the solar cycle in terms of prediction. Mark talked about predicting the solar cycle, how difficult it is. These are different models and how you're trying to auto-correct them. I need to update this plot with some of Mark's plots because they're much better. But the truth of the matter is, even predicting the galactic cosmic rays, which is the slowly varying solar cycle plots, doesn't predict the probability or possibility of solar particle events, which can kind of happen at any time in the solar cycle. Having said that, space weather from a point of view of satellite operators or from the point of view of sending astronauts, you need to know all aspects of space weather, not just the solar particle events. In fact, the GCR are the highest energy, hardest, most difficult to shield against, and those are the ones that if we had a solar minimum, like a very deep solar minimum, if solar minimum was a few percent deeper than normal, that has significant implications for astronauts that we would send to the surface of the moon, for example, or into deep space. But just as I mentioned earlier, predicting solar particle events, they happen at all times in the solar cycle. The 2017 event was deep in the middle of the solar cycle, and yet it was the largest event that we'd seen to date. So it's very hard to predict when these solar particle events happen. The question is, are they going to be hard events, and what do we have to do to protect against them? So I think the exciting thing that that is happening, and over the next going forward into the future, having the different constellations of satellites, we still have Stereo A up, we have Solar Orbiter, we have Solar Probe. We're going to have, RAD is operating on Mars, MAVEN is operating on Mars. All these assets are in different longitudinal locations. Together with all these assets, we're trying to understand and learn and study what determines whether a particular event would propagate 180 degrees in longitude to the far side of the sun, or just be focused like an ice cream cone and only have a 60-degree directionality. So, thank you very much.
Thank you very much. That was a very nice talk. Interesting subject. Anyone for questions, please? Yep.
Excuse me. Thank you very much. I think also it's necessary to mention of STIX instrument aboard SOHO.
Yeah, absolutely.
In the case of May events, because on May 20, they had a huge hard X-ray event on STIX.
Oh, great. So STIX is still operating?
Yes.
Okay, fantastic. Yeah. So.
And another question, also related to STIX, is that on the Earth, we had the CEP event on June 11, sorry.
Yep.
On June 11, and the position of Venus, where is solar, and Mars was similar, so I think you should expect the event on Mars.
Yeah, so I showed a plot with some of the Forbush decreases that we saw on Mars in June.
Yeah.
That's this dip right here. So we didn't see it as a very hard event, meaning it wasn't in terms of MEV energy levels. It wasn't.
Okay,
it wasn't hard.
I see the huge
Could have been large
here, but
yeah.
it's still possible to subtract background and see some enhancement.
Yeah.
Because you will know exactly the time of the event if you look on STIX.
Absolutely. No, that's good. Thank you very much.
Thank you.
Thank you. Alex?
Yeah, that 180-degree, extension in longitude is kind of puzzling me because, for SAPs, we see lots of them coming from the west, behind the west limb. And so the idea is that, well, you have energetic particles kind of traveling along the Parker spiral, right? So it's kind of hard to fit that into that picture that now you see something that is, 180-degree opposition to Earth, and it's not in field lines, right? So that might indicate that our kind of idea about the SAPs needs to be revised or looked at because it's kind of hard to understand.
Absolutely. I agree, 100%.
Maybe the last question, Robert?
What it also means is
sorry.
you could have an event on the backside of the sun and we have no idea it's happening, and you have astronauts on the moon and they could be affected by it.
I think there's also UVM on board of the MAVEN spacecraft. Do you also see like opportunity to utilize this data or related to those observations?
Yeah, so I didn't have it in this package because I only had 15 minutes, but I have another presentation which combines the MAVEN and RAD data, and it actually is a really good combination of the two missions, because MAVEN focuses on the lower energy solar energetic particles. They also have, that image of the aurora that I showed from this earlier event. There was also aurora seen in the May event. And so MAVEN has assets to view these solar particle events from a different perspective that is complementary to what we're seeing on the surface. And so the combination of those two actually helps us to really understand, from a vantage point far from where the Earth is, the nature of what's actually propagating around.
Okay. Thank you very much. Thank you, Don. And I also would like to thank at the same time for all the speakers this morning, because this was the last session, so thank you. And see you later in the afternoon. I think, Sarah, you are chairing it, yeah?
Okay. Hi, Emilia, and hi, Teresa, and hi, Berle. All of you are there.
Yes, hello. Do you hear me? Just checking the voices. Okay.
Yes, hello
Okay.
here.
Okay.
Okay. Okay. See you then.
Yep. See you.
They are there.
So just very quickly, Cristina, do we have the permissions to share our screens?
Okay, hi folks online. So we're just gathering here, about to start. And yes, we can hear you. I think I heard Emilia and maybe also somebody else.
Teresa.
So Teresa's here, great. And Ferry?
Yes, I'm here as well.
Okay, marvelous. Okay, so we have 3 online, but we're going to start with our first speaker. So first, let me welcome you to this session. So we are continuing now the session of the heliosphere, and we're going to start. And I'm Sarah Gibson. I'll be chairing. For all the speakers, I will give you 5 minutes, and please be aware that 5 minutes includes your time for question and transition. So that means don't go right up against the edge, and I'll give you another little nudge at 1 minute. And our first invited speaker is Stuart Bale, who's going to be talking about an expansion-driven Alfvén wave dynamo generates mean magnetic field in the solar wind.
See if I can make this thing work. So I'll wait for the slides. Thanks very much for the invitation. I'm happy to be here. My first time in Cape Town. Coming, okay. Okay, so this is work that we've been doing with Parker Solar Probe data. I'll tell you just a little bit about the spacecraft. People, I'm sure, have heard of it. And it's still a little bit mysterious to us. We think we've got a solution for it, but it's apparently kind of a fundamental result. And it includes many people. I've got an author list of, 100 or something, so I didn't put them up here, but my primary collaborators on this are Lorenzo Mattiini and and Jonathan Squire and some of my students. Okay, so to remind you about Parker Solar Probe, actually almost all of the data I'm going to show you from this talk is from our instrument that we call FIELDS. So FIELDS is basically 2 fluxgate magnetometers mounted on a boom behind the spacecraft. We have some plasma wave antennas, voltage probes that are in the plane of the heat shield, and then a lot of electronics inside the spacecraft that do digital signal processing from DC to about 20 megahertz or so. Parker launched in 2018, August of 2018, and this is scaled a little bit funny, but this shows you the the timeline of the orbit of Parker Solar Probe, and so we're really deep into the mission now, as you can see where the "we are here" thing is. I think that's relatively accurate. We've had 6 kind of orbital phases with different perihelion distances, which are listed along the bottom there. And we're coming up in November, on November 6th, to our final Venus gravity assist, which will pass within 400 kilometers of the surface of Venus. So we'll fly right through the ionosphere of Venus, which will be pretty exciting. And then on, I think, Christmas Eve, we have perihelion number 22, which will have its perihelion distance at 9.8 solar radii, so from the sun center, so 8.8 from the photosphere. So we're getting into more and more exciting part of the mission, of course, because we're getting lower and lower. It's also getting more and more complicated because we're approaching solar maximum, and so the measurements aren't clean solar wind measurements. Often they're full of CMEs and transient structure. Okay, so a thing we've been looking at since the beginning of the mission is the radial scaling of the magnetic field, right? So notionally, the heliospheric magnetic field, the background magnetic field, let's say, has a 1/r² scaling. It's just flux through a sphere, right? So it has its origins at a source surface, let's say, where it's entrained in the wind. So it loses the magnetic field loses out over the wind at the source surface. Then it's dragged outwards, and so you expect a kind of 1/r² scaling of the field. Very simply, this is an image from a paper by Mike Schultz from the early 70s or mid 70s that I'll come back to, but that's the point. And so we've been looking since the beginning of the mission to see the scaling of the field. And my student Sam Badman published this paper, 2021, looking at encounters 1 through 5. So if you go back to that orbital plot I showed you, this is all stuff above 27.9 solar radii. And so what you've got is a plot of, I guess this is what you call the simlog plot. It's log B, signed log B versus radial distance in AU now. And the solid lines that are plotted over the top of it, the red and blue solid lines are positive and negative polarity 1 over r squared scaling. Okay, so for the first 5 orbits, at least, 6 orbits, it was really apparent that it seemed apparent that we had 1 over r squared scaling. So remember, and you heard already from Alphonse earlier today, that we also see these things we call switchbacks, right? So switchbacks are large amplitude delta B over B of 1, order 1, Alphane waves. They're essentially incompressible Alphane waves that have steepened to become very nonlinear, okay? And you know that you don't see these things very often at 1 AU. At 1 AU, there were a couple papers by Jack Gosling published, 20 years ago or so, showing things that we now recognize as switchbacks. But generally, the magnetic field at 1 AU is very compressible and turbulent. It's just a turbulent field with compressibility in it. Okay, so you might see that kind of evolution. So this is the same data from that same paper by Sam. The top panel shows histograms of the radial field times r squared, right? So these should be essentially constant if the field is scaling like r squared. And in the top panel, or the left-hand side, sorry, top left is Parker Solar Probe below 0.3 AU, and the top right is all of the Parker Solar Probe data from those orbits. And you can argue here that this is, essentially a well-peaked histogram, that it's a constant value with some spread, and that spread includes the switchbacks. And then you can see as you go to, and the mean value here is about 2.5 nanotesla per r squared, per AU squared. On the right side, you can see all the data as well, and you have this sort of the same mean value, but it's spread out a little bit more, right? So there's some evolution that's a result of the switchbacks growing, in fact. And the bottom panels show stereo and wind, so that's 1 AU data, okay? And they have values that are a little bit bigger, in fact, 2.7, 2.9, and much broader, okay? So the switchbacks, which are, the field, which is basically a radial field with switchbacks in the inner heliosphere, has evolved to be a turbulent field. But you can also see that the peaks of these things are higher, 2.7, 2.9. It depends a little bit on how you sort the data, where you are in the solar cycle. But at the time, we thought that was insignificant. We thought that the 2.5 and 2.7 are pretty much the same thing. So these are for the same intervals of data. Okay. Then on encounter 12, we started to notice something very different. This is a time series of data. The top panel is the magnetic field magnitude. So you see it's pretty constant. The fuzz on top of there is incompressibility associated with the switchbacks, or is compressibility, but they're generally pretty incompressible. The next panel down is the radial field times r squared. So now you can actually see it's decreasing as we go into the inner heliosphere, right? It's clearly decreasing. And then we hit the heliosphere current sheet and come out the other side. All that fuzz on top of there are switchbacks. Those are all inversions of the radial field. The panel below that is the same data as above. It's BR times r squared. Now it's cleaned up to try to remove the switchbacks. So we make little histograms of the field and find the mode value, the peak value of that distribution. And you can see very clearly that it's decreasing as you go into the inner heliosphere. The panel below shows the tangential, the T and N components, so the components transverse to the radial direction of that same data, okay? And the reason we show that is because my first feeling about this, and actually from fitting this behavior, is that it goes like 1 over r. BR times r squared goes like 1 over r, right? Which means that this decrease in the field as you go inward goes like it has a dipole-like behavior. Okay, so it appears to be like a dipole, except that it's always reducing the field. Okay, and so if you look at and by a substantial amount, if you look at the top panel, you're looking at the field magnitude, and the little dotted line up there, if I can keep my at the top, is the value that you would expect if the field were constant at r squared. So the reduction in the field is on the order of a few hundred nanotesla. So it's huge. It's a huge reduction in units of nanotesla. Okay, so if this were a dipole, my first feeling from fitting this thing was that because it had a dipole scaling, that maybe this was some in situ measurement of a dipole field associated with the solar magnetic field. But in that case, you would expect to see tangential components, right? I mean, you're never going to go right down the throat of the dipole and see only the radial component. You would expect to be slicing it at some angle and see some tangential component of the dipole, which in the ecliptic plane should be the primary component at solar minimum. And so you would have expected to see in the T and N directions a field, a static field on the order of that 200 or 300 nanotesla that are missing. And we don't see that. All we see is the switchbacks. So the tangential components are essentially zero, average zero, with switchbacks on top of them. Another thing to note in this bottom panel is because Parker moves very fast at perihelion, it cuts through a lot of longitude, right? So this is not a, we're going in close to the sun, but we're going in Carrington coordinates. We're slicing through, in this case, 120 degrees of longitude through that little perihelion pass, right? So you would, there's no argument essentially that you're going down the throat of a dipole and seeing only the dipole component as a reduction. Okay, this is even more dramatic way to show the data. So this is now BR times R squared as a function of distance. Okay, so you can see the straight lines along here are the asymptotic values. Actually, these are asymptotic values in this case, 3.7 or something nanotesla per AU squared. And you can really see the decrease in the field as you go inward very clearly. And the solid lines that are fitted through there are fits of a dipole reduction of the field. Okay, so for a long time we puzzled about this. Because of this dipole-like behavior, this 1 over r cubed reduction of the field, we struggled a little bit and we're looking for a way to explain this as some kind of remnant of the solar magnetic field below us. Then we started looking at more and more data. Okay, and so now we see it everywhere. Okay, these, you can't really read these. These are the orbits 1 through 17. The first several orbits, it was very difficult to see, but as we got to lower altitudes, each one of these things, you see a reduction of the field as you go in, of BR times R squared. So it's ubiquitous now. I've seen it on every orbit since maybe 6. Where we started to get deeper in the heliosphere. By the way, we don't have the last 2 orbits of data. They're still on the spacecraft, so we can't really go much further than this. Okay, so one idea that we had was that this was since the heliospheric current sheet is generally at perihelion, right, or near perihelion, we had an idea that as we approach the heliospheric current sheet, maybe the field was getting weaker because as you go through the heliospheric current sheet, the field goes to 0. But to remind you that we're going, essentially 60 degrees through the HCS and then 60 degrees out the other side. So it would be an enormous scaling of the field reduction. But that didn't appear to be the case. So we did an analysis looking at the angular distance to the HCS as a function of BR times R squared, basically, or the R component of that. And there's nothing systematic in that. I mean, there's a lot of scatter, of course, but there's nothing systematic. So we don't think it's associated with the HCS, at least not on the large scale. And then we wondered if this could be somehow related to the missing flux problem. When you take a magnetogram and you do an MHD simulation of the evolution of the solar wind, you find that the values that you measure at 1 AU don't correspond to the appropriate values of the surface field of a magnetogram. This is the so-called missing flux problem from the solar magnetic field, or the solar wind magnetic field. So we did a comparison with some MHD simulations. These were generated by Pete Riley. And so we have, what you see is a transition from, on the left-hand side, the MHD simulation, the prediction of the MHD simulation of the BR times R squared out into the solar wind, and then where you see the abrupt break and all the action, that's the actual solar probe data. And I think we have here some different epochs, right? This is orbits 1 to 5 or something, 5 to 9, and then 10 to 15 on the right-hand side. And so you can see the missing flux problem in there. The mismatch between the MHD simulation and the actual data is the missing flux problem, but we're not approaching it in any sense. I mean, it's still a problem at our altitudes. So we decided that our problem is not an important contribution to the missing flux problem. That is maybe still something systematic with the use of magnetogram data or the quality of magnetogram data. And this is a comparison with the mass simulations too, where we've scaled the MHD simulation to account for the missing flux problem, the open flux problem. And so what you see is the dashed line, I guess, is our data, and the solid line is the MHD simulation data. And so we see an HCS in about the same place. We see sort of the same behavior. And importantly, in the panels, in the green and orange, which are the T and N, or N and T components of the field, neither one of us sees a dipole field below us. The MHD simulation does not see any remnant of the dipole, of a solar dipole at these altitudes, and neither do we. So we finally convinced ourselves that we're not seeing a reduction of the field as we go inward, that what we're probably seeing is an increase of the field as we come outward. And okay, this is that same plot again. And now we also see that it kind of levels off where beta, the bottom panel is beta, and the scale is over here. The dotted line is beta is 1. So we're starting to see this when beta approaches the value of 1, right, where the MHD alphane waves become more compressible, essentially. Okay, and this seems to hold now for all of the encounters. So what's going on? Okay, this is kind of an ugly plot. The top panel just shows you the magnitude of B, the magnitude of the total field, not just the radial component. So the total field is doing the same. It has the same behavior. So what's going on? So what we think is going on, okay, so this is just to say what we don't think is going on. We don't think this is a distortion of the solar surface that would have been captured by the MHD. So that's why I had this plot in at the beginning, just to show you that, when you think of PFSS, for example, we think of a spherical source surface. And so for a spherical source surface, the field should be radial to the source surface, right? So if it's a sphere, then it's 1 over r squared everywhere. If that sphere is distorted, then the field lines will be normal to the surface, but not necessarily simply 1 over r squared. But that should have been captured by the MHD simulation, and we didn't see that. We also have decided that it wasn't proximity to the heliospheric current sheet. We considered a little bit, reconnection well below us, and the HCS could reduce the field, and you might have some expanding depletion, but that doesn't square with the large angular extent of the phenomena, which we now think is purely radial. Okay, so then we started to think about the switchbacks, and instead of being a depleted flux as we go inward, we now think it's an amplified field as we're going outward, as the switchbacks grow, right? So to remind you what switchbacks are, they're just alphane waves. So if you look at, this is from a figure by a paper of Lorenzo Mattiini's, look at the panel on the right. This shows you where the magnetic field is, B naught, let's say, right, is the magnetic field, and there's a radial direction. It could be aligned with the radial. But what we're finding, the incompressibility associated with switchbacks is a constant field, including both B naught and delta B, okay? And this is, at least to me, a little bit mysterious, but this is what we see, is that the field conservation, the incompressibility of the field, is B naught and delta B together, okay? So that means that as delta B grows, if you look at this panel, it grows perpendicular to B naught, the tip of the field has to stay on that sphere, or on that circle, right? Because it has to be, B plus B naught has to be conserved. And so the tip is deflected, and so you have a delta B, which is in the anti-radial direction, which is what we see, a deflection away from radial. And of course, that gives rise then to a delta V, since delta V is perpendicular to delta B, that gives rise to a delta V radial, which is outward, which is what we see as well for the switchbacks, which is why they were sometimes called jets in the solar wind. The field switches backward and the velocity switches outward, and you have an impulsive outward jet. And the tip of the total vector has to stay on the sphere, okay? But as that alphane wave is propagating outward, at least if it maintains its WKB behavior, it has to conserve wave action. And you can show on a piece of paper, there's a paper from Joel Holvig in 1974, that means that delta B over B naught has to grow as you go outward. It has to grow like square root of r, okay? So in addition to delta B over B naught growing by conservation of wave action, by WKB, the sphere is getting smaller, right? Because the field itself is actually decreasing as you go out. And so the sphere is getting smaller and delta B over B is growing. And so it starts to fill, the field starts to fill the sphere, right? And that's the phenomena that we see in switchbacks. And you can take that simple scaling and show that pair of scalings, WKB, wave action conservation, and the decreasing field, and you can show, and this is just a simple calculation of an analytical calculation done by John O'Squire. The dotted line is 1 over r squared, and B is total B. Or the blue line is total B. So you can show that during the interval where the switchbacks are growing, before they become fully or relatively compressible, where beta is equal to 1, that there's an increasing behavior of the field magnitude. And so we believe that this is what we're seeing. And so one prediction of that is that the field, the bulk of the field should have the behavior of the blue line, but the radial component, the average component, the radial component should remain like 1 over r squared. And we've also recently confirmed that. So the red line is the field, the amplitude of the BR field, and the most probable value of the BR field, and the black dots are the average value of the radial field. So think of a distribution, a probability distribution that has a peak and an average. The peak and the average become separated. The average is the solar field, and the peak is the sphere being filled up by the fluctuations. And so we see that BR, average BR looks like a 1 over r squared. Yeah, I think I have maybe one more slide. And you can look at individual histograms and sort of see this as well. I think that's all I have. So that's my conclusion. So the conclusion is that the magnetic field is weaker than in the inner heliosphere, is weaker than the expectations of 1 over r squared scaling. And it's a big effect. It's a 20% effect. It's a few hundred nanoteslas. It's 10 times, about 20 times the amplitude of the field at 1 AU. This effect is not consistent with a simple PFSS scaling or with a full MHD scaling. It doesn't solve the missing open flux problem of magnetograms. It's not consistent with proximity to the heliospheric current sheet, but we do think it's a microphysics result. We think that it's basically the growth, the evolution of switchbacks of large amplitude nonlinear Alfvén waves into mean field as a function of altitude to sort of fill the sphere and become the magnetic field of the solar wind in the outer heliosphere. So it's kind of like an alpha dynamo process operating on the scale size of Alfvén waves. And I think that's all I have. This is just junk. Okay.
Thank you very much. Very interesting talk. So do we have any questions?
So you mentioned that you are not considering this to play effect in the open flux problem, but 20% is a significant effect, right? So
it's a significant effect, but you saw on the MHD things, we're still off by a factor of 2 probably. Where is that? So I don't think it solves the problem.
It might play some role, but not.
That's right. That's right. I think I would claim in the end that it plays a small role, but it doesn't solve the problem as stated.
Okay.
That's right. That picture, right?
Other questions? Any questions online? Oh, we have one over here.
We have one.
So I'm not familiar with the PSP, but I have one question to ask you. Can PSP detect the neutral atoms?
Neutral atoms. Not thermal neutral atoms. I think there have been some. Oh, neutrals. No, I was thinking neutrons. No, we have no neutral atom detection capability. No.
Thank you.
High energy neutrons, yes, but yeah.
Anybody else? Okay, if not, let's thank Stuart again.
Thank you.
Okay, our next speaker is Amelia Kelpoa. And Amelia, are you online?
Yes, can I share my slides or is it?
Yeah, you should be able to.
Yeah, I'm now able.
Okay, so Amelia is going to be talking about multi-scale structure of interplanetary coronal mass ejections. Take it away.
Okay, thank you. I'm just confirming that you are seeing this well. Yeah. Okay, thank you. And I would also like to thank for invitation to give this talk. So today I will be discussing about the different structures that we are finding in interplanetary coronal mass ejection. So first I will go through a little bit about the background of these ICMEs, magnetic clouds and flux ropes, and then talk about the global coherence and internal structure, and finally then concluding with some turbulent properties in these interplanetary CMEs. And the motivation for looking at this multi-scale ICME structure is, so the first one is the space weather. So as we know, the coronal mass ejection and the interplanetary counterparts are key drivers of the geomagnetic disturbances. And it's related both to the large-scale structure and also these like substructuring that we are finding in them. And then the shocks driven by these solar eruption, coronal mass ejection, they are then accelerating these energetic particles that are also one of the major space weather hazard. And then, of course, it's this like interest as to these ICMEs as a fundamental physical structures, from them as these large-scale MHD structures to the turbulence that they are exhibiting, like the normal solar wind. And this is featuring these different scale sizes that we have with these coronal mass ejections. So first we have here the large scale structuring. So ICMEs, they are one of the most significant large scale heliospheric structures. And if we see here, there's the sun, then there's this ejecta related to this coronal mass ejection eruption. Then it's driving the shock wave, and then between the ejecta leading edge and the shock wave is the so-called sheath region. And here focusing on this ejecta and sheath part, and they are both like large-scale solar wind structures. So ejecta are on average at the orbit of the Earth. They have diameters about 0.3 astronomical unit, and sheaths are on average about 0.1 astronomical unit. And this is, of course, then also the scale where this energy injection in the solar wind turbulence cascade is happening. And then we go to this mesoscale range that is widely distributed in the literature. So roughly coming from this less than 0.1 AU to the about 100 kilometers like scales. And in these solar like ICMEs, they are exhibiting a lot of different structures like current sheets, different kind of the waves, reconnection exhausts, small scale flux rope, and this is also the scale where this MHD turbulence cascade is happening. And then come to these kinetic scales where also different kind of the waves are happening, current sheets and turbulent energy dissipation is taking place. And here I'm mostly discussing about these large scale and mesoscale structures related to the ejecta and the sheath region. And also emphasizing this different nature here already between this ejecta and the sheath part. So quite often these ejecta are depicted as these extended loops where both field lines are still attached to the sun. They might at some point like reconnect open either at the sun or when they interact with this ambient solar wind, while the sheath region is this plasma and solar wind that has been gathered and processed by the CME when it's like blowing through the solar wind. And here are different magnetic field magnitude and components, solar wind speed, temperature and density. And one can see here that this sheet and ejecta are quite different structures. So sheets are very like compressed regions with large amplitude field fluctuations, and variability, while ejecta have this smoother appearance. And then to this global structuring. So the key one here in the ICMEs, or not all of them, but like comes soon, like about 1/3 of them are showing these signatures of the magnetic cloud, that is observational signature, featuring the enhanced magnetic field, smooth rotation of the magnetic field, and low temperature depressed plasma beta. And the physical configuration of them is that of the magnetic flux robe. There's a lot of these different type of models of them that I think Teresa will soon tell you more details about. And then, like just mentioned, the magnetic clouds, they are not all ICMEs, but about 1/3 of the magnetic clouds or ICMEs have these magnetic cloud signatures. And this plot here shows the time from 95 to the 2015, and then the percentage. So the blue dots are rays of magnetic clouds to all ICMEs, and the red ones are rays of the shock driving ICMEs. So let's focus here on now on these blue dots, and this green one is the sunspot number. So one can see that the fraction of the magnetic clouds, it's anti-correlating with solar activity with the sunspot number. So meaning that more complex structures are occurring at solar maximum, while when it's solar minimum condition, then nearly all of these ICMEs in solar wind observation, at least close to the Earth, are magnetic clouds. So something either intrinsically or in the solar wind, probably both, is distorting them more in the solar maximum. And like it was mentioned in the Spiros talk earlier today, it's kind of like believed that all of these CMEs, when they are launched, they are having these magnetic clouds or flux robe, but it's more than this evolution and these kind of the geometric factors, how we are observing them, that we are not like seeing not all of these ICMEs are magnetic clouds. And then about global coherence of the magnetic clouds, because we often have this picture in mind that they are these nice, beautiful, coherent loops in the interplanetary space, but there's plenty of these studies that have highlighted that they might lack this global coherence. So this is the example of the Charles Farrugia paper, where there's 3 different sampling points of the flux robe, and they shock normals, and one can see that this orientation of this flux robe in one single magnetic cloud can be quite different depending on the longitude of this spacecraft. And there have been these studies like Chris Owen, where they made this point that because the ICMEs are so big structures at the orbit of the Earth, about 20 to 30 degrees in longitude, they are encountering structured solar wind, so the different parts evolve differently in the interplanetary space. So kind of like emphasizing this probable lack of coherence on the large scales. And there was also this recent study made using this new heliospheric fleet. This is a study from Erika Palmerio, and it had more of this spacecraft, but here's examples showing from the Bepi Colombo and the Parker Solar Probe, the magnetic field, magnitude and components, and then this magnetic field latitude and longitude and fluctuation. And one can see here the same CME impacting these both spacecraft. And despite they were quite close to each other, so almost radially aligned, almost the same radial distance from the sun, and only about a few degrees in longitude separation, one can already see some differences between these ejecta. And this is a study from the Noe Lucas, where they studied the scale length in the magnetic clouds. So this shows one example. This is the magnetic field north-south component measurement at Wind and ACE spacecraft that are separated by these mesoscale distances in the solar wind. And then they took many of these ICMEs, 21 in total. So this shows here the correlation between the magnetic field observation at 2 spacecraft in this magnetic cloud part. And this is the non-radial separation between the 2 spacecraft. And this allows then to calculate this scale length of the longitudinal coherence as the extrapolated distance of the zero correlation between the measurements of these two spacecraft. And they found that in particular for the magnetic field components, it was much smaller than the magnetic cloud length scales. So kind of they suggested that the magnetic cloud has this coherent core, but then the distorted outskirts. And this has been also looked in this or noticed in this interplanetary observation. This is one of our earlier studies where we kind of separated these interplanetary ICMEs in multiple parts. So having here the shock, then followed by this sheet, and then there's found this magnetic cloud, but it's only the small fraction in the larger region that is having these typical ICME signatures that we in that paper called like magnetic cloud front and rear region, and made also the suggestion that these front and rear parts are magnetic cloud or like part of this original flux robe that was erupting from the sun, but then like disturbed by the interaction with the ambient solar wind. And it was actually it was a statistical study, and it was quite a large fraction of these cases that we found to have this clearly this like separate core region in these observations. And then the same study was done by Matti Alalahti for the global coherence, but for the sheet regions. So comparing these 2-point measurements between wind and a spacecraft. And what they found was that sheets are less coherent than this ejecta, but then they are more coherent than the normal solar wind or this background solar wind. So emphasizing this, that these sheets are embedding global fields, but have also this higher frequency fluctuation that are much more localized. And for the sheets, this is basically like emphasizing this large variability from the shock to the ejecta leading edge. So this is the same figure as before. This is a figure from one of our studies where we studied the space with the relevant sheet parameters. We were compressing all the sheets to the same duration and then made the superposed epoch analysis. So mainly this plot here is featuring this one, that the sheets have quite large variety in these parameters, so having like much larger this interquartal range than the solar wind before or after the sheet in the ejecta. And then it's interesting question also that how could we define or quantify this complexity in these interplanetary CMEs in the sheet or in the flux robe? So here featuring 2 ways. So one was presented by Camilla Scolini's papers, where they looked at how these magnetic field hodogram rotations are changing between like 2 spacecraft and the flux robe orientation. And she has studies where they like analyze how this flux robe type is changing. And then we have some recent work where we have used the measures from the complex for the information theory, so permutation entropy and Jensen-Shannon complexity. So we have analyzed different solar wind structures and found some interesting differences. And this is showing the result in the complexity entropy plane for large number of magnetic clouds. There are 2 colors are actually showing the different, or 3 colors are showing different time scales. But the basic message here is that they show quite plenty of spread in this plane. So it's interesting question that would these kind of the measures be also used for characterizing the complexity in these events. And then finally going to these more turbulence parameters. So this is showing the intermittency in the interplanetary CMEs. So intermittency meaning basically this variability in local energy transfer rate or burst signals that can have in these turbulent flows. So related to these changes in this energy cascade or eddy sizes. And it can present the existence of these coherent structures in the data, or in the solar wind in this case, that are inherent to the turbulence or then present otherwise in the data, like for example, the current sheets. And this shows one plot from the work from Julia Ruotia, who is in our team doing her PhD thesis. So this is solar orbiter observation of one magnetic cloud here. So this is the sheet, this is the magnetic cloud, and there are here PDFs of the amplitude of the magnetic field change. And this dashed line here is the Gaussian curve. And the more these curves are then deviating from the Gaussian, so the more intermittent the time series is. And when they are close. And what was found here was that this ejecta, shown here by this like brownish curve, they are least intermittent, so they are closest to this Gaussian curve, and in particular when one is like going to the larger and larger scales. So this tau here shows the time scale of the fluctuation in the magnetic field. And we had some other studies looking this intermittency as well. So this was doing this so-called partial variance of increment that has been long time used in the solar wind studies. So it's taking also these fluctuations and looking this when it has the high value, this PVI, then it's said to be signature of this intermittent structure, like for example, the current sheet. And again, this tau here is the time scale. So this is 94 seconds, so about 1.5 minute time scale of the fluctuation. And this is the PDF of this intermittency. And here this black line is the upstream solar wind, and this colored line are two part of the sheets. And one can see that this sheet is like clearly more intermittent than the upstream wind. So kind of emphasizing that they should be embedding then these intermittent mesoscale structures. And then Julia Ruotia, she also made a nice study about these coherent structures in the sheet region that can be either swept from the upstream to the sheet or formed in the CME sheet region. So she looked small flux ropes and then the Alfvén waves, and she identified them based on these cross helicity and residual inertia and magnetic helicity. These blue lines are small flux ropes, and here so this is upstream, this is sheet, here light blue is small flux rope, here the dark blue is small flux rope, and these reddish curves are then Alfvén waves. And one can see that while these Alfvén waves are about the same or decreasing to the sheet, the number of these flux rope is increasing from upstream wind to the sheet. And this she found for several different of these time scales. And finally, about this residual energy and cross helicity, these are interesting turbulent parameters related to how the waves are propagating and how the magnetic and velocity fluctuations are in balance, and also important, for example, for the particle acceleration in these structures. And this shows here the superposed epoch analysis of the residual energy, and this is so-called rectified cross helicity. So normally the cross helicity gives the rays of the parallel and anti-parallel propagating fluctuation in the solar wind, and this rectified is fixing the direction to the sun. So when it's larger than 0, it's waves propagating away from the sun, and when it's negative, it means the waves propagating towards the sun. And when this value is 0, it says that turbulence is balanced, so there should be waves propagating in the both direction. And then this residual energy is giving the ratio of the magnetic and velocity fluctuation. So when they are close to 0, they are saying to be like equipartient, so equal amount. But here one can see, so this is a study made by Simon Wood from the University of Helsinki team. So here one can see that in the sheet, so it's decreasing from the ambient solar wind, and then having its minimum in the flux rope, and especially this rectified cross helicity is showing clearly more balanced values in the like leading edge of the flux rope. And there was also with Juska Soliento in our team doing a similar study. So he took the sheet and looked the residual inertia and cross helicity. So these are showing the same similar results. So in the upstream, the cross helicities are very peaked to the waves propagating away from the sun, and then this curve is flattening and being like most flattest in the ICME, so having the most balanced value. And this is also showing this residual energy that is mostly equipartitionate.
5 minutes.
Okay. And then this we are now ongoing study where we look in more detail how this cross helicity, residual energy, and magnetic helicity, how they are changing at the shock wave. So how much these changes between these different parts and different solar wind structures are mediated by what is happening at the shock wave. So this is the wind data. This is solar orbiter data at 0.31 AU. And here are magnetic field, velocity, density, temperature, and this is the sector of the magnetic field direction. And these are wavelet spectrograms. And one can see here in both of these cases that how the solar wind becomes more balanced from the upstream to the downstream of the shock wave. The residual energy becomes more showing the magnetic domination. And here in the bottom panel, these cyan lines, they are bounding the regions that fulfill the criteria for the Alphen wave, and these pink lines, those that are fulfilling the criteria for the flux ropes. And we can see that how this transition at the shock wave, it like kind of diminishes significantly the fraction of the Alphen waves, but then more of these flux ropes are forming or are existing in the downstream. But okay, this was the summary. So just emphasizing this multi-scale nature of the ICMEs and that it has these two different parts, sheet and the ejecta. And while ejecta are more coherent than the sheet, but both show mesoscale substructuring. And also these turbulent parameters are having different characteristics between the sheet and the ejecta. Okay, thank you.
All right, thank you. We have time for questions. Any question online? I have a question for you, Amelia. You showed a slide where you showed some longitudinal structure in the CME and how it really, we're saying that it doesn't follow just a very simple coherent structure. Do you have any other comments about how things evolve longitudinally? And I'm asking partly because of the conversation we had earlier today with the case of the May storms, where there were SEPs observed on Mars, which was, I think, very far away from the Earth, and how the longitudinal evolution during propagation, how that may impact things.
So was it this slide or?
I think it was the one we had like 3 different flux rope fits.
Yeah. This one, yeah, this Jet Alpha. Yeah, I think this is like sometimes quite amazing that how quickly these ICMEs or even this like flux rope change from one location to the other. So I think that's something that is now featured by these like previous and this current multi-spacecraft observation, that these can be surprisingly different even at like relatively small longitudinal distances. Of course, it depends, although like varies from case to case, but.
Okay, thank
and
you.
I think that's really the challenge for predicting the space weather and understanding these as structures, that you can have these big variations.
Other questions? If not, let's thank Amelia again. All right, our next speaker is Teresa Nieves Chinchilla. Teresa, are you there?
I am here.
Okay, perfect. Okay, so Teresa is going to be speaking today about lessons learned from the magnetic flux rope modeling. And we're just, I guess you're sharing your slides, right?
Yeah, here they are. If I'm able to
Okay.
play, let me see. Okay, starting now. Thank you very much for having me today in this session. I would like to be there physically and share with you in this presentation, but it has to be virtual. So I'm going to talk about the lessons that I have learned over the years about the modeling of magnetic flux rope. This work that I'm going to present today, the investigations, are not just mine. They are contributions from the Lassos group and many other co-authors. So I'm very thankful for them. In this presentation, this is the outline. I'm going to introduce and motivate why we are doing this investigation. And then after this motivation, I'm going to present a preliminary diagnostics of the flux rope geometry to understand how are they deviated from our preliminary idea. And then later I will introduce also the experiment about how far we are from distortion, so expansion, how important they are, curvature, or compression of the flux ropes. And now the ongoing investigation about the multi-point and multi-spacecraft challenge that we have when we try to put together observations from different observatories, solar heliospheric observatories. And at the end, if I can, I will conclude or bring some conclusions or lessons learned and final thoughts and remarks. So flux ropes in heliophysics are very critical structures because not just because they are easy to model, but also because they are the main responsible of the transport of helicity, magnetic energy, magnetic flux, and mass from the sun to away in the heliosphere when they are embedded in the interplanetary coronal mass ejections, but also in other structures within the heliospheric current sheets or even within the magnetospheres in the transport of this helicity and energy from the solar wind to the planet, to the ground base of the planet. So in general, we associate the flux ropes with the interplanetary coronal mass ejections, and this is going to be the focus in this work, but we can extrapolate the ideas to other flux ropes in heliophysics. Traditionally, flux ropes have been characterized by the in situ observations. In the 80s, here Burlaga and many others researchers observed increase in the magnetic field, as you can see in the plot, in the magnetic field magnitude, changes in the magnetic field direction that you can see in the components, but also in the autograms at the bottom of the plot. And associated with this monotonic change in the magnetic field, there were some characteristics in the plasma that display confinement in the plasma. And that's why these researchers brought the plasma physics laboratory flux rope models into the heliophysics. They have been working very well, but as we have more data, more information, and more observations, and we see that maybe we need to move from these models to something more adapted to the reality that we are trying to understand. So as I say, this investigation always has been starting from the in situ observations. And we start always from the simple case, trying to add the complexity as is needed and balance with the importance of this complexity. So originally what we have is a spacecraft crossing this large scale structure, like here. So we can make assumptions. We can say, okay, so the spacecraft is crossing just a small portion of this largest structure, so we can assume that it's a straight axis. We can assume also that there is no distortion. Let's assume that this structure is dominant in the ambient solar wind and remain circular cross-section, and the helicity or the twisting of this magnetic field lines around the axis are monotonic, uniform, and distributed equally in the whole structure. But however, the reality is different. As we bring remote sensing observations, we see distortions, and we associate these kind of dark areas, distorted areas, with the flash robe and the distortion on the flash robes. And numerical analysis also displays these nice colors, but also the complexity in the magnetic field lines that not always are very well organized and distributed along the whole structure. So how can we include all these ideas and discussions into the models? So let's take first, starting from the simple case, circular cylindrical, a small spacecraft crossing this large structure. I'm gonna, before finishing this motivation, I'm gonna bring a case that it was also in part of the discussion in the previous, in Emilia's presentation about the multi-spacecraft and multi-point, and the multi-point challenge that we are now more, they are very, very actual, right? Everybody is trying to understand and this, how multi-point can bring more knowledge in the modeling. So in this case, is one example, there are more, is work led by Sanchita Pal from 2023. It was a very complex case with three CMEs involved, one coronal hole, one CIR, and heliospheric current seed crossing. So it was, in this case, it was this event, or this period of events, were the main responsible for loss of many satellites on February 3, 2022. So the angular separation between, and I'm going to highlight just one of the events. During this period of time, we have wind and stereo A separated by 34 degrees, and solar orbiter was in between. There was observed in situ flash robe signatures, but wind and stereo A, as you can see at the bottom of the slide. Both of them were flash robes or simultaneous crossings. However, it was not crossed by solar orbit. The structure didn't cross, or there was no signatures in solar orbiter. And it brought the attention from Sanchita. Sanchita and their co-authors were trying to reconstruct or understand, looking at from the source to all the structures and all the heliospheric observations and in situ observations, trying to understand what was the source of these two flash robes. And in the conclusion, Sanchita, all the data and all the observations and all the modeling was leading toward to the fact that this was the same structure crossing the two spacecraft, highly distorted and curved in a way that it didn't cross solar orbiter. So my question is, what kind of forces can lead this kind of distortion in the flash robe? And it seems that the complexity of the heliosphere was the main cause. So this is the motivation, and let's go now in a stepwise, trying to understand the flash robe and how to model this flash robe in the heliophysics. The first thing is to diagnose flash robe geometries. So let's go to the data and see what the data itself tells us. And just to point out that this idea was also the source of a lot of investigations using machine learning techniques. And I'm going to talk about that, but I invite you to go and read this investigation, which is very interesting. So let's go in this idea to diagnosis flash robes and departures from the geometry, circular cylindrical geometry. The first thing that we have to do is to bring a circular cylindrical model. We can use any, but I'm going to use this model because we have built all the models based on this idea, which is just a geometry coordinate system and solving Maxwell equations and assuming just some kind of distribution in the current densities. So this is the model, and we need a we can use, as I say, any model. We can use a reconstruction technique that in this case provide information about the trajectory of the spacecraft and the orientation of the flash probe. And using the idea, instead of to reconstruct, to simulate synthetic data, we can actually evaluate the signatures of a flash probe with this geometry, with in any orientation or distance from the center. So we can use a front flash probe, perpendicular flash probe, or any variation of that. And we can simulate this data. And as you can see, as in the in situ and in the autograms, we see the rotation in the magnetic field components, and also in the autograms, the rotation in one of the planes. Okay. So using this idea and coming back to the real data, we can just visually compare and say, okay, how many of these events show signatures of flash probes? And you can see on the top that the first one is a case where it's very clear case of flash probe, almost 180 degrees rotation in the BY-BC plane. However, in the second case that we call F-, this flash probe can be almost a flash probe, but not completely rotation. In the third case, this is what we call F+, is a case where we have more than 180 degrees rotation. We can think about a spheromag, for instance, other kind of flash probe, but different geometry. And we have many other cases, not many, but some cases where we see more complex events. And in these cases, we cannot use the kind of geometry or any flash probe model as we understand them. So in fact, doing the statistics using the ICMEs observed by wind between 1995 and 2015, we observed that only 40%, it was almost 300 events, 43% of the events saw clear signatures of flash probes. And these deviations, F+, F-, were around 40, 36, 37% of the events, but some cases of ejected and complexity. So now, just focus in the cases where we see circular or at least flash probes with a clear axis and rotation. So let's now focus on them and trying to evaluate what is the distortion or expansion in these cases. How is the deviation from the circular cylindrical case? As we saw in the synthetic data, if we are thinking about circular cylindrical configuration, in any of the cases, a spacecraft crossing this structure should show a symmetric profile in the magnetic field strength with the maximum in the center. However, in this case, this is one example, we see this profile in the magnetic field strength, a symmetric profile with an increase at the front of the flash probe. Normally, this is not new, something that has been investigated for many years, has been associated with the expansion velocity. So in this experiment, what we did is to evaluate this asymmetry and compare with the expansion velocity to see how many of these events were actually related with the expansion. As we see here, we see one case where at the top on your here. I don't know if you can see my cursor. Anyway, so in one of the events is very asymmetric, and we see the velocity, the profile in the velocity showing a very high expansion within the two dashed lines. However, in the case on the right, we see that it's very flat, the magnetic field strength, and very flat, the expansion velocity, which is consistent with the idea that the symmetry is related to the expansion. However, cases like this, where we see very asymmetric profile with the compression at the front of the magnetic field, is also related with negative expansion. It's like something is compressing at the back, but maybe is also expanding at the front. So to understand these kind of signatures, the first thing that we need to have is a model with distortion. So we developed the model in 2018 where the distortion in this case is elliptical distortion, and the distortion is implemented in the coordinate system with this delta, which is the compression or the ellipticity of the cross section. But thing about this is not orthogonal coordinate system and requires a mathematical formulation, a new mathematical formulation to develop the model. We save this and we have the model. Now we have to evaluate also the expansion. In the expansion, there are two factors that we have to take into account. Now is the expansion itself with an aging, so a decrease in the magnetic field strength, right, with the time as the spacecraft is crossing, and also implementing the correction in the reconstruction technique. We did so. In this case, in the model, we implement both corrections in the circular cylindrical model and in the elliptical cylindrical model. And we came to one event that it was published in this paper in the first Parker Solar Probe observation of two interactive coronal mass ejections. In the second one, display a very clear asymmetry in the magnetic field strength, and we test the model. And it was a test, not a fitting. In this case, just focusing at the top in the top layer in the magnetic field strength. On the left, we have the circular cylindrical model. On the right, the elliptical cross-section model. And we have dashed lines with no distortion included, no expansion included, and the bold line is included the expansion. In the test, we were testing and proving what kind of expansion will require. Obviously, with no expansion, in the case of the circular cylindrical model, there is a symmetric profile. So we require introduce expansion, and to get the profile in the circular cylindrical that is the observed, we require an expansion of 375 kilometers per second. Just to, obviously, in this is Parker, it was a 0.6 astronomical unit. There are no statistics about the expansion at this radial distance, but at 1 AU, the average expansion velocity is 25 kilometers per second. In the case of distortion, the distortion with elliptical cross-section, the expansion velocity required to reach the profile observed in the magnetic system, 125 kilometers per second, closer to the average value at 1 AU. So in this case, we will require, to explain this kind of profile, we will require elliptical cross-section and expansion. So let's go now to another experiment. In this case, we need to understand if these kind of profiles are because of distortion, curvature, or compression. And again, to do so, the first thing that we need to do is to have a model to test the profiles, to get the synthetic data. So building over the previous models, we go now to a global model where the distortion is included in the cross-section, but also the curvature in the global structure. In this case, the curvature is in the toroidal mode, as a first approach, is just a torus. So in this case, in the cross-section, we were more ambitious, and we were trying to replicate observations from remote sensing. As you see, the elliptical case, but we have also this peanut shape, we have compression at the front, and this kind of heart shape that is also very well observed in remote sensing observations. So here, the exercise to create synthetic data is a little bit more complex. Your right and your left, you have the circular cross-section, and the colors display are the RTN components. So we have, just to exemplify the signature, the in situ observations, we have two spacecraft, one crossing through the center and one at the 0.5 impact parameter from the center. So it's circular. We have the symmetric profile in the magnetic field strength in the black contour plot, and the BR is flat, as you can see. And if we compare, let's go to compare with the distorted or compressed case, we have this asymmetry in the magnetic field strength. Either we cross through the center or we cross halfway to the edge of the flash robe. And in the case of the BR, it's very interesting that the BR is not flat as used to be if we assume circular cross section. Another interesting point is the BN component. In the case that we have circular cylindrical geometry, the structure goes from north to south very nicely. But however, in the case that we have compression, the time in the positive side is shorter than the case in the negative side, and also is more abrupt the transition from north to south. If we add curvature, 5 minutes, yeah, okay. If we add curvature, we also observe at the back of the magnetic field strength, we see this increase, and also we can observe different signatures in the magnetic field components. As we add more features, we can evaluate the different profiles in the strength and in the magnetic field components. We did this exercise to compare visually compare with the real data. We have here one case with impact with compression at the front, and the simulate data, dash lines are circular, cylindrical, the bold lines are in the distort cases. And we compare now on your left with the real data, 2 events at the top and the bottom. The asymmetric profile seems to be very, very similar to the synthetic data. We observe in the green line, which is the BN, that the crossing is very close to the center, to the front of the structure, and is more expanding at the back of the structure. And also in the first case, we see in the BR component these changes also that are related with the compression and what we saw in the synthetic data. So we are now, at this point right now, we are trying to embrace the challenge of these multi-point observations and trying to put all of them together. So this is an ongoing investigation right now. And this is part of the work that Andreas will feedback from the reviewer and hopefully very soon publish. In this case, using the same idea in the coordinate system with different coordinate system growing from there, this model implement distortion in the radial axis, but also distortions in the toroidal axis. So it means that we can have different distortions along the toroidal axis, and we can have also different distortions within the same cross section. So this is very interesting because in this case we can observe very force-free core in the flash robe, and however more non-force-free a structure at the edge of the flash robe, which is associated with the distortions and interactions with the ambient solar wind. And just as I promised at the beginning, conclusions, if any, no many, because we are learning as we are walking into the new data and new methods, new observations, and we are trying to embrace all these new things, new observations into a new numerical models into our model in order to describe the nature of the flash robes. So something that I didn't talk about today, but it's also very interesting, is to evaluate the forces in these flash robes that are, with these models are possible, and then to understand the forces and the implications in the stability of these structures in the solar wind. The debate about the global morphology is obviously on the table for all of us as we are learning, as we are having more data, and obviously we are right now looking forward for Solar Orbiter to get out of the ecliptic plane and provide a new perspective of the CMEs from other point of view. This is it. I'm ready for any question. Thank you.
Thank you, Teresa. I think we have time for one quick question. Yeah, Mark.
Very nice talk, thank you. So with regard to your first point, do you have any guess and sort of the latest on what that implies about geo-effectiveness? Are sort of coherent flux ropes more likely to cause strong geomagnetic storms?
So coherent flash robes are obviously more geoeffective. So in order to predict this, the orientation of this flash robe and the implications of the distortion, compression, curvature, this is the main challenge that we are facing with these kind of models. So right now we are investigating also from remote sensing how can we quantify this coherence or the implication or the relationship between distortions and coherence structures as observed by heliospheric imagers. But I don't have a good guess right now. I don't know if I answered your question, Mark.
All right, thank you, Teresa. Okay, let's thank Teresa again. And our final talk is a contributed talk, and it's by Ferle Sterken, who's going to be talking about the dust-heliosphere connection. And I think we have your slides, right?
Yes. But can I move the slides?
You can share if you prefer.
I can share, okay, yeah. Is this working?
Yes, we see it.
Okay. All right. Yes, so this is going to be about the dust-heliosphere connection. Just a small introduction. I'm the leader of a ERC starting grant group in the ETH in Zurich, and we do research on dust in the solar system. We focus on trajectory simulations, spacecraft data reduction, instrument calibration, and mission concept design, and of course we also do teaching. In this talk, I will talk about synergies between the heliospheric and dust sciences on two scales. One is the global scale, and the other one is a local solar wind scale. I will talk a little bit about common use of instruments and then go to the future missions. So let's first go to synergies between the heliospheric and dust science on a very large scale, and let's zoom out from 1 AU towards outside. You can see here a plot of the solar system basically moving through the local interstellar cloud towards the G cloud, and we are moving at 26 kilometers per second. Because of this motion through the clouds, we have basically dust and gas coming in the solar system. And as you all know, we have a heliosphere around us built by the solar wind. And basically the dust will move through the solar system, and so we can do research on it locally here in space. But the dust and the heliosphere are very coupled, as I will explain later in my talk. Some of the dust will make it and some others will not make it. Now, we do not know that much about the heliosphere. There are a lot of questions still not answered today, and some of them are, for instance, what the shape of the heliosphere is. Is it a spherical, is it a cometary shape, or is it more a croissant? We don't know why the heliosheath, the interaction region with the interstellar medium, is so thin, and why Voyager hasn't seen a change in the magnetic field when it flew outside. The dust is also very fascinating in interstellar space. It's the building block of planetary systems, and it's important in the interstellar medium, also for astrochemistry, for instance, and also important for astronomical modeling. So they both have their own, basically, field of research, but they're actually also connected. The dust is used to learn about the heliosphere. It can be used as an extra constraint, like galactic cosmic rays. It's often an overlooked.
Verla?
Yes, sorry.
Oh, sorry. There's your slides. We're seeing something on the bottom. Is it possible to switch to a form? I think extended.
Can you extend your screen, please?
Extend my screen.
So we're seeing your notes as well.
Oh.
You want to
I think
present
just
view,
up at
so
the
go
top.
other one.
Sorry.
No problem. It just makes it kind of small for us here.
Isn't working.
Share your screen again. You're not sharing a screen now. You stop sharing.
Yeah, sorry. Share. I'm just wondering if I should share, perhaps I should share just this screen here instead. Is that working? Is this better?
No, still wrong. So on your laptop, share the second screen. Yes, click at the bottom where it says there's a small like T here at the bottom. Just click F5.
Oh.
Make it full screen.
I see.
Yes, am I still sharing or?
You're sharing.
Okay. Am I sharing now the presentation?
You're sharing.
Okay, that's the right one.
Perfect.
Yeah. That's it better now.
Okay. All right, sorry. So where was I? Here, right? Yeah. Okay, so the dust is we can use the dust for learning about the heliosphere as some kind of constraint. It's often an overlooked part in heliosphere physics, and we also need the heliosphere for the dust science. There are a lot of science questions concerning the dust and the heliosphere together, which we have summarized here in this paper. Synergies between interstellar dust and heliospheric science with an interstellar probe. And I will not go over all of them because it's too much, but I would like to invite you to have a look at this paper. Now, why is this dust coupled to the heliosphere? Well, because the dust that flies through a plasma will be charged. There's electron and ion currents going on the dust. There's photoionization, and there's also secondary electron emission. And a charged dust particle that moves through a magnetic field will experience a Lorentz force. The bigger the dust is, the smaller the charge to mass ratio will be. And so very small particles that have a small mass will have a high charge to mass ratio and will be influenced much more. So the big dust, 1 micron and higher, will just go through the solar system, while the nanometer dust will be flowing around the solar system. That's how they are coupled together. As you all know, the solar cycle is moving on, and the magnetic fields in the heliosphere are also changing with that through a 22-year cycle. And the dust that can make it in the solar system, so not a nanodust, but an intermediate-sized dust, will focus and defocus with respect to the ecliptic plane or to the solar equatorial plane. The next focusing phase of the dust is in 2030. So ideally, you want to have instruments in space then in the ecliptic plane in order to measure the interstellar dust. And if we miss this, the next 11 years, there will be defocusing, and then the next time we can measure it again will be 2052. The very small dust will have very different trajectories. It comes here from the left to the right, and it will create kind of density waves in the solar system. This is for 70 nanometer, and then super small dust, 30 nanometer and smaller, will be blocked outside of the heliosphere, depending also on the solar cycle sometimes. Now, the small dust is very much higher in density. So here you see the size of the dust, nanometer to micrometer. And on the vertical scale, you see the amount of particles per cubic meter per differential size. And you see that there is a line here from the astronomical data. You see and that the spacecraft, these dots here, are not able to measure everything, and that is because of the heliospheric filtering of the dust in the solar system. But if you would have an instrument on an interstellar probe, kind of a Voyager follow-up mission, then we would be able to measure really orders of magnitude more dust. So that's why we would like to have an instrument there. So the dust and the plasma is coupled together. We have the plasma properties that we need for the dust to put it in our simulations, but also opposite, by using the dust, we can constrain the heliosphere, for instance, the size, or help them constrain it at least. So there is a need for missions with plasma, magnetic field, and dust detectors together. Now let's go to the local scale. There are Jovian dust streams coming from Ios volcanoes, and there are also very small, tiny Saturnian dust streams from Enceladus oceans. And these particles are typically 10 to 20 nanometer large, and so they are known to be reacting to solar wind structures like gravitational interaction regions. Just keep that in mind for the following few slides. But we will first go to another mission, something we've been doing this year recently. That is the WIND mission that is flying out L1. WIND has plasma wave antennas on board, and whenever a dust particle hits the surface of the plasma of the satellite, it will create a little plasma cloud, and that little plasma cloud can be measured with the plasma wave antennas. So it doesn't even have dust instruments on board, but we can still measure the dust impact. And you see here horizontally the time and vertically the amount of particles per day. And you see clearly that there is a yearly variation going up and down here. That is because we go once a year with the interstellar dust flow and once a year against the interstellar dust flow, leading to less and more flux in total. And you also see here the focusing phase and the defocusing phase. So even with indirect methods like a plasma wave antenna, we can measure that. But the funny thing is that we also have a solar rotation frequency in those data. So you don't see it here by eye, you only see the yearly frequency, and here there's a yearly peak, but also at 27 days there is a peak, and then at 6 days there's another peak, but that's because of instrumental reasons. So we've been wondering what can cause it, and we've been looking at when does it happen. It seems to happen more when wind is moving against the interstellar dust stream, so interstellar dust must be part of the signal. And it happens more when there's a focusing phase of the solar cycle, which is logical because there's more dust that focuses. And it turns out that it correlates with the gravitational interaction regions, but we don't know exactly what the size of the dust is and what exactly causes it. Then we also had a look at all the SIRs within the CIR, and we have less impact during these events, these transient events. And the stereo mission has been finding the same thing, but the question is, will we see the same with a dust instrument or not? So we actually need a big dust instrument to confirm this finding. But this is very new, it's still in press, so it will come out very soon. The next synergy is the common use of instruments. As I said before, plasma wave antennas can be used for dust measurements, but also spacecraft like Gaia and other interferometric missions, when they are hit by a dust particle, they will move a little bit, and we can use that for our data. And also opposite, we need plasma data for our, for instance, dust surface charge calculations in order to know, for instance, how fluffy the dust is. There's a whole lot of questions, again, that only can be solved if you have both kinds of instruments on board of the spacecraft. And that's why we are advocating for future missions to have both together. Some of these are those, the Lunar Gateway, the L4 mission, Interstellar Probe, and Dolphin. So first of all, as I said, in 2030, there is the focusing phase of the solar cycle. So we would like to have something in space, and we approached ESA. And ESA is going to do a phase next year for putting a dust instrument on the Lunar Gateway, which is the next International Space Station, but that's going to fly around the moon. So it's going to be in the free solar wind. And yeah, so that's hopefully going to happen in the early 2030s when the dust is focusing in the solar system. We've been doing our homework. We've been doing some simulations, and as you can see here on horizontal axis is the time, vertically is the amount of focusing that there is. And so for 50 nanometer, if it gets through the heliosphere, it will focus up to 10 times more.
5 minutes.
Yeah, thank you. Then we have the L4 mission, the Korean Space Agency that just exists since a couple of months, is very keen on flying a mission in the L4 point, especially to focus on observing the sun for energetic electrons that will go out. But in the run direction of the orbit, there is space for a dust detector. So that would be an ideal mission to do this research on, for instance, CME dust interaction. Then we have Interstellar Probe, as I already explained. This is kind of a follow-up mission for Voyager. Hopefully, it will come one day with a dust detector on board. And the last one is a mission proposal that we have proposed to ESA. It's called Dolphin, the Dust Observatory, to study the local interstellar cloud, interplanetary dust, and the heliospheric interactions in our neighborhood. This is also a mission that will combine dust and heliospheric sciences together at a slight inclination out of the ecliptic plane. So concluding, I've been showing briefly synergies between heliospheric science and cosmic dust science due to coupling of dust and the solar wind, but also due to common use of instruments and data. We have a focusing and defocusing phase in the solar cycle for dust, and especially in the 2030s, there's a next opportunity. There are solar transient events in the dust data that we can see, and I think there's a lot to explore in the future. Future projects are underway, especially the Lunar Gateway and the L4 mission, but hopefully also Interstellar Probe and Dolphin. And yeah, these are the main conclusions, and I would like to invite you to have a look at these papers. The first one is about the synergies, and the other one is still going to be published this year at the end of the year. And the third one is about these transient features. Thank you.
Thank you very much for this nice rounding out of our multi-messenger heliophysics today. So we have time for one question, maybe? Questions online? Okay, in the interest of time, I am going to cut it short because we do have some posters downstairs, but thank you again. So we have posters downstairs, and please come back at 3:30 for the PhD prize talks.
So we start the last exciting session of the division day, which is the time during which we give the prizes to our PhD winners and honorable mention winners. Our first talk will be by Shuto Beki. He is an honorable mention for 2022, and he will talk about the sun's differential rotation. So Shuto, here, go up. Here is your certificate, and congratulations.
Thank you.
Come here.
Thank
Okay.
you.
So I'll give you 10 minutes. At 10 minutes, I wave, and you have 5 more.
Okay. Great. Thank you. Hello. So my name is Yuto Beki. I'm a postdoc at the Max Planck Institute for Solar System Research. And so I'm very honored, I'm very happy to receive the honorable mention for IAU PhD Prize of the Year 2022. So today I'll be quickly reviewing my PhD thesis works. So here's my PhD thesis, the front cover, with the title Theory of Solar Oscillations in the Inertial Frequency Range. It is a collection of a couple published journal papers, but in this talk, I'll be mostly focusing on this particular chapter about the baroclinically unstable waves and their implications on the sun's differential rotation. So let me begin with a brief introduction. So the sun's interior can be studied with helioseismology, which analyzes waves or oscillations seen on the solar surface. And traditionally, high-frequency acoustic modes, whose restoring force is pressure force, have been used to do helioseismology, and which has been really successful so far. On the other hand, low-frequency modes of inertial oscillations, whose restoring force is Coriolis force, were also predicted to exist in the sun's interior for more than 40 years, but they hadn't been observed until very recently because their oscillation periods are very long, several months, and very long-term observations over many years are required to detect them. So in 2018, Lipton et al. Reported the first observational detection of the equatorial Rossby modes, a particular class of inertial modes of the sun. And later on, in Gizon 2021, we have further extended Lipton's work and successfully detected a bunch of other inertial modes on the sun. And this was, their mode identification was made possible with the linear with the numerical computation of the linear eigenmodes of oscillation, the sun's differentially rotating convection zone. This was done in Becky et al. 2022. The detected inertial modes of the sun include not only equatorial Rossby modes or modes at the equator, but also modes at middle and high latitudes. The solar inertial modes tend to have very low velocity amplitudes on the order of 1 or 2 meters per sec. So why do we need to care about these low amplitude modes? Because we found that the solar inertial modes have a very important diagnostic potential for helioseismology. Let me show you an example. For example, our linear model shows that the radial profile of the equatorial Rossby modes are strikingly sensitive to the values of the turbulent viscous diffusivity nu. And also, the propagation frequencies of some non-toroidal inertial modes are found to be sensitive to the so-called superadiabaticity, which measures the tiny deviation of the entropy stratification from the adiabatic state. We note that these, both of these parameters are very important unknown parameters in the sun's deep interior, but they can be poorly constrained by traditional P-mode helioseismology because P-modes are not sensitive to these parameters. All right? So in this talk, I will focus on the high latitude inertial modes. Because they are particularly interesting, they have the largest velocity amplitude among all the other observed inertial modes. In fact, this M=1 mode corresponds to the polar spiral flow pattern already reported by David Hathaway and Lisa Upton a decade ago. But at that time, these velocity patterns were somewhat misidentified as giant convection cells. But in GIZON 2021, we have shown that they are actually global modes of oscillation because when you look at the power spectrum as a function of frequency and latitude, you can see the power excess at all latitudes characterized by single frequency. So there are standing waves, the global modes of oscillation of the whole convection zone. And this minus 90 nanohertz in the co-rotating frame falls into the inertial frequency range of the sun. So we call them high latitude inertial modes. All right. In Becky et al. 2022, we have carried out a linear eigenmode analysis to show that these high latitude inertial modes are unstable. They become unstable with the presence of latitudinal entropy gradient. What does it mean? It means that they are baroclinically unstable. So when you look at the eigenfrequency of the M=1 mode, the growth rate becomes more and more positive with the increasing latitudinal entropy variation. And when you look at the eigenfunction, if the background is non-baroclinic, the mode doesn't show any spiral pattern, but it begins to show a spiral pattern just as we observe at the surface when the sufficient baroclinicity is included. And the dispersion relation of these baroclinically unstable waves, unstable modes, can nicely explain the observed frequency of the high latitude inertial modes. Okay? But why do we need to care about these baroclinically unstable modes or baroclinicity in the sun? Because it is closely related to the sun's differential rotation. So, the sun's differential rotation is known to deviate from the well-known Taylor-Proudman's theorem. And this deviation is thought to be maintained by latitudinal entropy gradient via the so-called thermal wind balance. And this thermal wind balance approximation tells us that the polar region of the sun must be slightly hotter than the equator by 5 to 10 Kelvin. And this temperature difference is very, very small compared to the million-degree background. So it is an extremely difficult task to measure this tiny latitudinal temperature difference by direct observations. But you see, we have shown that the newly discovered inertial modes, high latitude inertial modes, are strikingly sensitive to this small temperature difference. So they can be used to infer this latitudinal temperature difference. Okay. But the difficulty is that these are unstable modes, so nonlinear simulations are required to understand their mode amplitudes. So what we did is to carry out a 3D mean field simulations of the solar large-scale flows, and we adopt the mean field approach to circumvent the convective conundrum. And for the differential rotation and meridional circulation are driven by the so-called lambda effect. So for these mean field parameters, we took the values from Rempel 2005's 2D model. And here is and what we did is to carry out a series of nonlinear simulation with varying baroclinic forcing by changing the model parameters which control the entropy generation rate. And here is the representative simulation results. You can see that our mean field model simulates very nicely the baroclinically unstable waves. And you can see that the observed spiral pattern around the poles can be very, very nicely reproduced. The main results is that So the plot on the left shows the relationship between the latitudinal temperature difference and the amplitude of the M=1 mode. From case 1 to case 10, I increased the baroclinic forcing. You can see initially that as I increase baroclinic forcing, the pole to equator temperature difference increases and the M=1 mode amplitude increases. That makes sense. But when the mode amplitude exceeds some threshold value, the pole to equator temperature difference begins to decrease. This is because of the nonlinear feedback by the modes. According to our analysis, we found that the modes transport heat equatorward from pole to equator to reduce the imposed latitudinal entropy gradient of the background. And this is to limit the further excitation of the further baroclinic excitation of the modes. Okay? And we also found that these baroclinically unstable modes have profound implications on the sun's differential rotation. So you see, so the plot shows the relationship between pole to equator temperature difference and the latitudinal differential rotation amplitudes. You can see that in 2D models where the non-axisymmetric modes are excluded, you can actually increase the differential rotation as much as you want by changing the model parameters. But this can never occur in 3D case because of the back reaction of the modes. The baroclinic modes limit the pole to equator temperature difference, and this drives the additional meridional flow to affect the differential rotation. So there's an upper bound, maximum possible value for the latitudinal differential rotation allowed by baroclinic instability. So let me skip the last slide. And, where's the summary slide? Yeah, so here's a summary slide. So in my PhD thesis, we have first reported the observational detection of various inertial modes of the sun, and then we report the numerical models to study them. We show that these low amplitude inertial modes can be used to infer the previously inaccessible parameters, such as turbulent viscosity and superadiabaticity. And we also show that some inertial modes play a dynamical role in the sun. This is totally unlike the conventional acoustic modes. We show that the high latitude inertial modes are baroclinically unstable. They regulate the baroclinicity and control the sun's differential rotation. All right, so overall, I think a series of my PhD thesis works have paved a new way to probe the sun's interior with inertial modes, which we call the inertial mode helioseismology. That's all. Thank you very much for your listening. Thank you.
Now it's working. So thank you very much. It's very nice work. I like to see that these Rossby modes do something. They are dynamically important. I wanted to ask you about this observational work of Krishnendu Mandal. I don't know if you have seen the Mandal and Hanasoge.
Yeah,
this year. And they observed this M=1 mode deep down till 0.4 of the solar radius.
0.8?
4. So it is in the radiative zone still. So I don't know if you have some thoughts about that.
Our models, I don't have a plot, but our model shows that these high latitude modes extend very, very deeper down. And their mode velocity amplitude peaks at the base of the convection zone or slightly below. So yeah, I think it's very interesting to compare with the...
Yeah, it could be even deeper. And what the question that I have that is not certainly to your work, but in general is what is generating this mode deep down? Why is it?
I can mention that our linear model, which nicely reproduced the baroclinical modes, M=1 mode, doesn't have the radiative interior actually. So I think the convection zone dynamics is enough to excite these baroclinical modes. But we will be also working on the inclusion of radiated interior. Yeah.
Thank you.
Thank you. Thank you.
So we now change subject and we go to April Saade, who is our PhD at large prize winner for 2023, and she will talk about the deflection of solar eruptions. So, April, congratulations. And we get the picture. Okay. 10 minutes.
Okay, hi. Thank you, first of all, for the AIU for this prize. I'm from Argentina, and there the university is free of charge. The best of our universities are free of charge. And without that condition, I wouldn't be here today. And I think this is important to mention because nowadays we have, since last year, a government that is dismantling the public university and the scientific system. So that will mean that thousands of young people would not have the opportunity to be here in the future. So I think that it's important to realize the privileges that all we have about being here and how those privileges take us along the way. So now let's go and talk about how to deflect solar eruption. So first of all, solar eruptions are dynamic events that take place in the sun. They have signatures in the solar disk as flares or filament eruptions that they propagate to the outer heliosphere as coronal mass ejections or CMEs. And we all know that those CMEs can have effect in the space weather, can affect the Earth and other space missions around the heliosphere. And then it's very important to be able to predict their arrival to Earth or other places. And one of the things that we need to know is where they are propagating to. So it happened that not all of them propagate radially from the sun. They can be deviated from their source region, origin. And one of the main causes of that is the magnetic field environment that surrounds the source region of ejection. So for example, we have coronal holes that literature said that can deflect away of the place the coronal mass ejections, and then we have low magnetic energy environments like pseudo streamers or the Helmholtz streamers, where the CMEs tend to go to. So the question is, how is every feature in the sun affecting the evolution of a coronal mass ejection or a solar eruption to deflect their propagation of direction? And as the solar environment is very complex, we have different things over there. So for my PhD thesis, we investigate the action of these particular things. So we did some works about magnetic energy, some works about coronal holes, and some work about pseudo streamers. I will focus mainly in the two last of them. So we combine two techniques. We analyze observations. What we wanted to do is to track the position of the prominence, mainly the prominence material, which is the source region of the coronal mass ejection later in the eruption. And we use type pointing techniques using multi-view points observations to know exactly the 3D coordinates of them, to compare them with the magnetic environment. And then we also use MHD simulations, 2.5D simulations, in which we have a magnetic flux drop, like the force model, the catastrophe model, and we add a magnetic structure in the vicinity of it, so we can isolate the scenario and understand how each parameter of this magnetic structure is affecting the evolution of the flux rope. So first, let's talk about the influence of coronal holes. So here you have the works about it, like if you want to take a look of all the things that we did there, but I want to focus in the dynamic behavior that we found, which is general for all the cases that we investigated, all the parameters. So by changing the alienation of the polarity of the magnetic flux rope to the coronal hole, we have found two cases. One in which the foot points are aligned, and we have the formation by the addition of these two fields of a null point in the other side of the coronal hole. And if we have an anti-aligned case where the foot points of the flux rope are toward the coronal hole, then we will find a null point toward that section. So in the case that we have the aligned polarity, we have a deflection of our flux rope against the position of the coronal hole, as is expected from the observations. However, if we have this case, we will have first a deflection toward the null point and then against the coronal hole. We found some events to compare this where this was going on, what that happened. So the thing here is like, I want you to take from here is we have null points that attract the flux rope, and then we have the action of the open field lines of the coronal hole that push the flux rope away of them, like channeling them in the other direction. And then we did works testing the influence of the pseudostreamers. And then we use again our MHD model where we add the structure of a pseudostreamer in the vicinity. And in this case, we have much complex situations because the pseudostreamer is a more complex structure than the coronal hole. And then, for example, we have a previous null point from the pseudostreamer. And then we have a secondary null point from the addition of the flux rope. By changing different parameters from the pseudostreamer and from the position of the flux rope, we can have different scenarios. So from here, we again found different dynamic behaviors, but they all have something in common, and is that generally the flux rope travels toward his local null point and then toward the spine of the pseudostreamer. Except in these cases where, as you can see here, we have these three cases are in the outside part of the pseudostreamer, and then the flux rope, instead of going toward that spine, is traveling toward its own kind of spine. So we have here null points and a different change in the topology, and that produce different dynamic behaviors. And also we found that some of the cases didn't erupt, and that was mainly because we changed the strength of the magnetic cage around them, and the flux of that magnetic cage was key to understand whether they will or not erupt. So also, just to show you about one event that we analyzed in this paper is the cartwheel event. That event was not well understood. It has a deflection toward a coronal hole and against the gradient of the magnetic field, so it was kind of difficult to understand why the event was behaving in that way. With the models that we had, we track this event with the 3D coordinates, we reproduce the environment, and then we model it by changing the parameters of our simulation. And we were able to reproduce this double deflection and, in general, the behavior of the event. So by understanding the topology, the position of null points, and the gradient of the magnetic field, we can, again, have the same behavior. So from these works, for me, the most important things, okay, I am running, sorry. I have a lot of time. Okay. So the most important thing for me is that null points play a key role in deviating the magnetic flux ropes. And then it's important to understand how they are connected to the flagstrobe, and then how is the topology around it. So what we are doing now is to use multi-viewpoint observation of NASA and ESA missions. So like by, again, reconstructing actual events, and from the understanding that we have from these works, we are trying to define proxy for the deflection to estimate the deviation of deflection. Because for now, we don't have anything like that. We have, for example, here for this event, one of the things that there are presented in many works is like that solar eruptions will travel toward the minima of energy, but it's not always what happened. And here we have like how is, for example, the path of this gradient that is nothing to do with the real path that is more similar to this proxy that we are defining. And I hope to publish it soon so you can go and look for it. So that's all. Thank you very much. Yeah, I'm sorry.
In your simulation, whether the initial configuration is in equilibrium or it starts from any arbitrary state?
Sorry, can you repeat the question?
I mean, at the perform the simulation, whether the initial configuration is in equilibrium.
Yeah, no. We start from out of equilibrium flagstrobe. It's already eruptive flagstrobe. And yeah.
Okay, just put an arbitrary location and release it and then let it go.
Yeah. So if we have just the flagstrobe, it is already eruptive. It will erupt radially. And then we add this kind of different magnetic structures, the coronal hole and everything, and we change. All of these studies are multi-parametric. So we change the distance to the different magnetic structures, we change the different parameters of the flagstrobe and the strength of the magnetic field, for example.
Yeah, so you just focus on the deflection of the ejection by the coronal hole, the other kind of structure around.
Yeah.
Okay.
Yeah, in these works, we change, here we change many parameters, we have the dependence of those parameters too. Yeah, this is just one of the results that we have in those papers. Yeah.
Thank you.
Thank you.
Very nice talk, thank you. So in the observations that you use, is it primarily like UV that you're using to look at the structure of the plasma, to find the nulls and to find the deflections?
Yeah, we use all the UV channels and also the coronagraph. And in the cases, for example, for this event, the Cargill event, it's possible to track also the CME in the lower corona. As you can see here, it's very nice to see in 195 channels. So we track both the prominence material in every channel and the CME structure. And we compare, so these cross sections are the cross section of the CME GCS model, and the dots are the type pointing of the prominence material. So we, yeah.
Do you ever, or do you have plans for, or have you used coronal magnetic field extrapolations? And part of why I ask is because I know like Nishu Kano did a study of a pseudostreamer with a null point, and we were able to use the UCOMP or the COMP observations to see that the potential field extrapolation really doesn't get it anywhere near.
Yeah.
So I imagine it would be challenging to use extrapolations because even the MHD models tend not to do that great of a job. But if you could do a prediction not just of the trajectory, but of the CMEs, in advance of the eruption, right?
Yeah. So yeah, for example, here you can see how these are not perfect matching. We are just trying to reproduce the behavior, right? But then, for example, for this new thing that we are doing here is we are using PFSS just because it's available and it's already there, and it's the most simple case. The thing is that any extrapolation is not taking into account the action of the CME. We are just looking at the static action of the coronal field previous to the eruption. And also we cannot take into account the action of it, just maybe the foot points, and if they are not reconnecting, we don't have many information. So we are trying to do from here, have a first idea of how or where CME will deflect just by knowing the magnetic field around it. And yeah, it will be very interesting to check to see if better extrapolation of the magnetic field give us better results about where this is going to. Yeah. Thank you.
And we change subject again. And now we go to the Boyotica Samanik, if I say it properly, who will talk about opening new frontiers in solar radiophysics. And he has been awarded the honorable mention for 2023. Congratulations. Thank you. So at 10 minutes, I wait, and you have 5.
So good afternoon, everyone. I am Devojyoti. I did my PhD with Divya Oberoi. He is here, and National Center for Radio Astrophysics in India. And currently, I am an associate Jagadi Fellow at Johns Hopkins University Applied Physics Laboratory. So today, I will be talking about mostly about my thesis work and also something which I am currently doing in continuation of that. So with the last decades, there are two great instruments at the radio wavelengths came out, which are the precursor instruments for the future square kilometer array, which is going to be the world's largest radio telescope. And these two instruments you can see in this figure. This is placed in two different parts of the world, one in Western Australia and another is in South Africa here. And today I will be talking about which are new science cases that these instruments will open up and already opened up and also going to open up in the future. So first I will start with how the sun looks like in the different radio wavelengths. So in this figure you can see from very high frequency at about 25 gigahertz to at very low frequency about 24 megahertz. And you can see the sun looks very different at different frequencies. And the reason is that these radio emissions from the sun is mostly coming from the base of the solar corona or close to the chromosphere at very high frequencies, and at very low frequencies it is coming mostly from the higher coronal heights. And depending on what frequency we are looking at, it's different kinds of emission mechanisms plays a role, and also we can see different structures we can see the similar structures at different frequencies in a different way. Now, in terms of the different kinds of emission mechanisms at low frequency, this is mostly dominated by the plasma emissions from the solar plasma, coronal plasma. But at higher frequency, we get both the thermal emission from the plasma as well as the plasma emissions, and as well as the gyrosynchrotron emission from gyrosynchrotron or gyroresonance emission by the electrons gyrating in the magnetic field. So for the two instruments I will be talking about, it's particularly observing at these two frequencies, about 80 to 300 megahertz, and another instrument that is observing at about close to 1 gigahertz. So in this particular regime, it is very interesting because this regime, the optical depth for plasma and Bremsstrahlung emission crossing each other, and also the gyrosynchrotron emission can be seen. But still, there are several challenges in observing the sun. It is a very bright source, but still there are several challenges. Means even few minutes ago in the poster session, someone was asking why you need such a large telescope like square kilometer array like telescope, very sensitive telescope, to observe this bright sun. The reason is when we are looking at the solar radio emissions, the brightness temperature of different types of radio emissions varies by orders of magnitude. For quiet sun, it can be about 10 to the power 6 Kelvin brightness temperature, and for when some radio bursts are happening, it can go up to 10 to the power 13 or 14 Kelvin temperature. And not only that, if we look at their polarization properties, they can less than 1% for the emissions coming from quite some thermal emission to almost 100% in case of some kind of solar radio bursts. And not only that, if we look at their time frequency variation, they are very dynamic and shows different types of temporal and spectral variations, and also different types of spatial structures. So what we actually need to observe the sun at the radio wavelengths to extract all the critical information that these observations can provide, we actually need very high dynamic range images, because both these bright emissions and the very faint emissions from the quiet sun and coronal mass ejections, they can present simultaneously. And at the radio wavelengths, we cannot use a coronagraph to block the bright emission to look at the faint emissions from the CMEs. So what we need very high dynamic range images. Also, we need very high fidelity. So whatever we are measuring from the images or observations, those are accurate. And also we have to do this in very small temporal and spectral span. So because the emission is itself changing over small spectral and temporal domain. So we need very spectropolarimetric snapshot images. So I very quickly go over this slide because to give you a glimpse that why this radio observations of the sun is very challenging. Because in the radio wavelength, we don't make images directly. What the radio interferometric imaging do is, it is a Fourier synthesis imaging technique. So we have multiple radio telescopes on the ground and mainly measuring the Fourier transform of our sky. And to produce the image of our sky very accurately, we need to make the Fourier sampling in the Fourier space very densely. And if we have the very dense Fourier sampling that you can see, we can actually very well reconstruct the source. And ideally, one needs the Nyquist sampling, but if we have very good coverage in the Fourier sampling, so we will have very good contrast in the image, that is the high dynamic range, and also it will increase the image fidelity. So to achieve that, we need an instrument which have extremely good spectroscopic and snapshot sampling in the Fourier space, because the solar emission is changing over small time and frequency, as well as we need very precise calibration of the instrument and atmospheric effects. So both of these criteria, the first requirement is well satisfied by this instrument called the Murchison-White Field Array that primarily I have used for my PhD thesis. So this instrument consists of 128 antenna tiles, that is, you can see a small small dipole stations that you can see here, and distributed about 3 kilometers of region. And that provides very dense UV cover, very dense sampling in the Fourier space. And that allows us to produce very high dynamic range spectroscopic and snapshot solar images. And similar case is for the high frequency part of the square kilometer array precursor instrument that is called Meerkat, that is here in South Africa. And that also provides this very high, very dense sampling in the Fourier domain. But the next challenge was because the radio interferometric imaging and calibration is very challenging, and most often the radio observation have not been used because of this difficulty, because one needs sufficient learning curve and expertise to make the radio images. So one of the primary goal of my thesis is to make a state-of-the-art, user-friendly and end-to-end pipeline such that you can get science-ready images from this excellent instrument directly without having detailed knowledge about the instrument calibration and radio interferometric calibration and imaging. So that we have developed during my PhD named this pipeline called PAIRCURS, and it can produce spectroscopic snapshot solar images of having dynamic range about 10 to the power of 5. And also the polarization calibration is of the order of 1% accuracy. And this is fully automated, robust, and user-friendly without detailed knowledge of radio interferometry one can use. And it is written in such a way, developed in such a way that it can be easily adaptable for the future SKO. So now I will give you some glimpses of new science result that was enabled by the MWA and the PAIRCURS that I've developed during my thesis. So the first, So first I will talk about the detection of the very low level of circular polarization from the quiet sun thermal emission. Then I will briefly touch upon the gyrosynchrotron emission from the CME plasma that one can use for measurement of the magnetic field from the CME plasma. And then I will talk about a very controversial topic in solar radio physics, that is about linear polarized emission from the solar active emission. So with the high dynamic range images, we have detected the circular polarized emission from the quiet sun thermal emission that I have shown you in this red box. And so this polarization fraction, it's of the order of 0.5%, and it is very hard to detect, but our precise calibration of which provides the accuracy less than about 0.07% allows us to detect this circular polarized emission from the quiet sun thermal emission. Now, what is the use of this? One can use this circularly polarized thermal emission to measure the line of sight magnetic field in the solar corona. And so we did a very preliminary analysis calculations. So we can measure the magnetic average line of sight magnetic field using this observation about 100 milligauss. And as also we have the imaging observations, so these measurements can be done in the spatially resolved way. But in this study, we have not included the propagation effect, and that is the current work we are doing. So this is one of the very straightforward way to measure the quiet sun magnetic field of the solar corona magnetic field using the circular polarization observations, and this opens a new way to looking at the solar corona. Then I will talk about this topic of linear polarized emission from the solar active emission. So in 1970s, it was detected many times, but after that, there is a consensus that no linear polarized solar radio emission can be seen at meter wavelengths because of the high differential Faraday rotation. And if detected, it actually challenges this decade-long assumption, but can also be used for measuring the coronal magnetic fields. And interestingly, this assumption now goes into the calibration of the instruments even for some recent work. But with the MWA observations and also simultaneously GMRT observations, we have detected this linearly polarized emission from solar active emission. So this image is from the GMRT, this is from the MWA, and the bottom image showing the linear polarized emission. Both of them have about similar polarization fraction. So this tells that these emissions are actually real, present, and the physical mechanism behind this emission is still under investigation, but it reopened a decade-old problem in solar radio physics. And this part I have already spoken about, I spoke in the IAU symposium, so I'm not going into details. But what I wanted to say, the gyrosynchrotron emission from the CME plasma can now be detected up to 10 solar radii, and the spectropolarimetric observations can be used from the gyrosynchrotron emission can be used to measure the magnetic fields. So the inclusion of the polarimetry into the picture can be used for robust measurement of the magnetic field. As you can see in this posterior distribution of gyrosynchrotron parameter, when we included both the strokes I, total intensity and circular polarization, it can break some of the degeneracies in the parameter space and provide much more stronger constraint on the magnetic field estimation. Okay. So I just not going into details about the meerkat because this is something I am going to start, and this we are doing very recently. So this is the first image we made using the meerkat, and it's exceptionally very nice instrument to make the solar images. And I'm not going into details of the whatever different science cases this can produce. It can give a large range of exciting science. But what I want to focus is the quality of these solar images this instrument can provide. So this left-hand image is a synthetic meerkat image produced using the solar, estimated using the UV observations. And this is the same time, the meerkat solar images observed using the same time. And qualitatively, if we compare the different morphologies between these two images, it's extremely well matches each other, even the small scale active region bright points and coronal holes, active regions, everything. So this is a new domain that we are now going, and we have also started commissioning these observations with the Meerkat. And I believe that the solar radio physics now entering into a new era with the SKO precursors, and in the upcoming days with the SKO it will provide much more new results. Thank you, and here is the references. You can scan for this. Thank you.
You start measuring polarization in radio, which was actually done in the past. How about the instrumental polarization? In optics, we had to deal with that in the radio as well.
Yeah, right. So that I talked at the beginning that the instrumental polarization is large, but the calibration of the precision in the instrumental polarization calibration is of the order of 1% that we can achieve with the pair cuts. So for the Stokes I to Q is about 1%, but for U and V it is much less than 1%. So that allows us to mainly detect or estimate this quite-some circular polarization, which is actually less than 1% level. Thank you.
And we changed subject again. So we are changing subject all the time. And we invite Robert Jarolin to talk about frontiers of artificial intelligence in solar physics. He's our PhD winner for 2023. Congratulations. Great. Okay, so I wait at 10 minutes, okay?
Thank you.
I wait.
I think that's the wrong one. So I can use the meantime to say that this is really, yeah, right. Well, in the meantime, let me express my thanks. It's a big honor to receive this award, and I want to thank the organizing, the committee for granting me this award. Would also like to thank my supervisor, Professor Astrid Veronik, and all my collaborators over the last couple of years that continuously supported me and that helped me conducting this research. And now I'm waiting for my slides, maybe. Okay, while we're waiting, the thesis title is Frontiers of Artificial Intelligence in Solar Physics. And today I want to give you basically an overview of my thesis, which is compiled of 6 papers, and I want to follow basically like 3 big topics in this. Okay, so maybe I can get the presentation. Yeah, perfect. Okay, thank you. So, as said, Frontiers of Artificial Intelligence in Solar Physics. I want to keep this more on a high-level application to really see the different fields where we can apply artificial intelligence for solar physics and to see the actual synergy between the 2 fields. For this talk, I will focus on 3 main topics. So for the actual thesis, there are more papers in it, but I want to give basically like an introduction to each of the individual topics and then a corresponding basically a corresponding example to see basically how neural networks and artificial intelligence can be applied for this corresponding field. So for the first one, I will talk about feature detection, then about image domain translations, and for the final part, which I think is the final frontier that we have at the moment, this is about simulations with physics-informed neural networks. So just as a quick introduction, when I talk about artificial intelligence, what I'm referring to is mostly the field of deep learning, which is the smallest subfield and the most recent one where we are working with neural networks, which consist of a large amount of free parameters and can be used basically to solve arbitrary complex problems. The basic principle that we only need here for this understanding today, for this presentation, is basically this concept of mapping between inputs and outputs. So what we can do with neural networks is basically we can make use of the free parameters and the aspect that we can basically adjust the parameters to fit any arbitrary function to basically learn a mapping between an input and an output. So we can use a corresponding data set of input and output pairs and optimize and adjust our weights of the neural network to find a mapping between those two. And this is a very universal approach where we can then use this trained neural network as a universal function approximator in that sense. So why is this relevant for solar physics? So we are facing more and more data, especially like, for example, with the SDO satellite, we are generating 1.5 terabytes of data per day. So it is required that we actually look more into automatic data processing methods because this is beyond human capabilities of analysis. We also have an increased amount of complexity in our data, which requires already trained observers. So having new methods that can further make use out of this data is also next step forward. And finally, computational requirements, both for the aspect from space weather, where we need time-critical solar monitoring, and also from the aspect of generating more sophisticated methods, which are extremely computationally expensive. This concept of deep learning, artificial intelligence can help. So in general, what is really important here is that with deep learning methods, we basically have new processing capabilities that enable us to address long-standing problems in a very novel way. And with this, I want to start with the first topic, which is basically this very simple image that I introduced of having a data set of input and output pairs, and then using a neural network as the general function approximator. So this application, the first topic, is for coronal hole detection. So this is the first example where we used neural networks for this application. And coronal holes appear as dark structures in the solar atmosphere. And they're the source region of fast solar wind streams. So therefore, they're relevant for space weather applications, but they also have a direct connection to the solar cycle, which makes them also interesting from the scientific perspective. When we try to, for this reason, there were multiple different methods already proposed for coronal hole detections, which were based, for example, on thresholding methods or clustering methods. However, there are also other dark structures like filaments, which are a different feature on the sun, which can be easily confused. So for this application, we wanted to build on neural networks to detect the coronal holes not based on a clustering or a thresholding approach, but to actually detect them based on their feature representation. So neural networks provide here the explicit advantage that they can detect objects by simply applying this mapping and making use of the shapes, edges, global relations, and also the multi-channel information. So this goes already beyond basically what we can do as a human observer. This neural network can actually make use of this full information simultaneously. And the method that we developed for this one is called Chronos, which is basically trained with pre-labeled data set where our input is taken from SDO AIA plus the magnetograms from HMI. And the output are the corresponding manually labeled coronal hole maps. And then we train this neural network with a certain set. And the advantage that we gain from this is that we can then apply this pre-trained network to the entire data archive and basically scan through the entire archive and obtain coronal hole maps over the full lifetime in a very consistent and robust way. And in this study, we explicitly showed that we can detect 98% of the coronal holes accurately. And specifically, we can see that the coronal hole maps that we obtain show this anti-correlation with the sunspot number. So they also have this long-term consistency. So this is really the important part here, that we have one single method that we can then apply over the whole solar cycle to obtain consistent coronal hole maps. And when we also compare this over smaller time scales, we can see that this is even more reliable than manually labeled coronal holes, where we still have certain jumps, while this method has the robustness to give consistent coronal hole detections over the entire solar cycle. So for the second application, this increases a bit in complexity, where we are talking about like image domain translations. So the main motivation for this topic here is basically the rapid upgrade of solar observations that we are facing. where we have observations from different instruments with varying quality, different instrumental characteristics, and most importantly, mostly no overlap or very limited overlap between individual data sets. But when we are dealing with long-term studies or studies that use multiple instruments at the same time, we really need to deal with a homogeneous data sequence. So here we use deep learning methods to translate between image domains and in order to homogenize data sets. So the method that we have developed for this is called instrument-to-instrument translation, and this makes use of the ability of neural networks to not only translate between individual images, but to translate between individual domains. So we train a neural network first to learn basically the domain of SOHO and SDO images, and then perform a translation between the individual domains. So we actually don't need an alignment of the data sets, but we can translate between them in continuous fashion. So this is what is shown here on the right-hand side, where we basically mapped the images from SOHO to the quality of SDO images. And we provide this basically as a general framework. So this is just one example, but we provide this as a general framework for instrument intercalibration. And in most cases, we have very limited alignment, but there are some cases where we can actually do a direct comparison. So this is what is shown here on the right-hand side. We can see in the left column the observations from SOHO, and then we apply our instrument enhancement or instrument translation approach to obtain basically images in the SDO quality, and on the right-hand side you can see the reference images that were taken at the same time when there was an alignment between the two instruments. And from this we can see that this provides an intercalibration, it also provides an image enhancement, and it can also take into account the differences in the channels. So this is really a new capability that we can actually better homogenize our data sequences through this approach. And especially when we look at this over the full lifetime of the instruments, we can see that we obtain a more homogeneous sequence when we apply this calibration approach instead of just using a baseline calibration method. And with this, I want to talk about the last topic, which I think is the biggest frontier, which is about using neural networks for simulations. And specifically, I want to talk about magnetic field simulations with neural networks. So far, I was talking mostly about the regime here on the far right, where we have a lot amount of data available, but basically no understanding of the underlying physics. Like, for example, the coronal hole detection. We don't know how actually the physics works of this detection scheme. Just from images to labels, there's no understanding of the physics, but we have a large amount of data available. But there's also this regime on the far left, where we have basically very little data available, but we have a full understanding of the underlying physics. And this is basically where we can use neural networks in a very new way to basically do data discovery by solving partial differential equations for a given boundary condition. And this provides an alternative to finite difference approaches. So I'm not going into full detail here, but what we are basically doing here is we are solving a boundary value problem with a system of coupled partial differential equations. And this enables us to basically discover new data. So the primary aspect here is what we are trying to do is we want to estimate the coronal magnetic field in this entire simulation volume based on the photospheric boundary condition. And we do this by applying nonlinear force-free model in terms of the divergence-free and force-free equation. In this case, the neural network acts as a function approximation, like this universal concept of having a function approximation of the magnetic field B. And then we can basically use this network to find a solution that satisfies both our boundary condition and the physical equations in order to obtain this magnetic field in the simulation volume. With this, we can apply this then to observational data. So here's an example when we apply this to this photospheric vector magnetogram from SDO HMI. And here we show the field line traces in comparison with the EUV observation, where we can immediately identify the central components, the central flux rope, as well as secondary flux ropes. And we can also observe here this eruptive structure, which becomes visible shortly before the solar flare event. This is also very computationally efficient, so we can apply this basically in quasi-real time over the sequence and can model with this the energy distribution, free magnetic energy over time, which has important implications for modeling basically this, the energy storage and release mechanisms. And specifically, we can see when those jumps here happen in those sequences that those align with the flaring history. When we look into more detail, we can actually see when we compare this with the integrated EUV emission over this time, that the depleted magnetic energy during this period aligns very well with the EUV observations. But what we wanted to do next here is basically to not only go for what we can already do with conventional methods, but we wanted to go basically beyond to provide more realistic nonlinear force-free extrapolations. And with this add-on study, basically, we tried to include additional chromospheric magnetic field measurements. The problem when we are dealing with chromospheric magnetic field measurements is that they are additionally corrugated, so we can't assume a flat surface. So here we can really make use of this flexibility of physics-informed neural networks, where we can first include an additional degree of freedom, where the model can adjust the single height surface to a corrugated surface, and this is then used in the next step for this extrapolation. So with this, we can make efficient use of all the observing capabilities that we have, and we can also include chromospheric magnetic field information into our extrapolations. And with this, we can apply this for data. So here you can see an example. This is the region that we're focusing on, where you can see this elongated flux rope here in the center. And when we compare this between a single height extrapolation from before and the multi-height extrapolation, where we also include the chromospheric magnetic field information here from Solis VSM, you can see that we obtain a much more twisted, elongated, and elevated flux rope, which is in better agreement with the actual observations that we have in EUV and in H-alpha. So in summary, what I tried to basically present here is this huge synergy between solar physics and deep learning methods. We can use deep learning methods like for simple cases like mapping functions to approximate based on our data sets and expand this basically to an entire data archive. But we can also use more advanced methods which enable us with new opportunities in terms of, for example, domain translations in order to achieve instrument intercalibration. We can also use neural networks for simulations. In this case, physics-informed neural networks provide basically state-of-the-art magnetic field modeling. So the most important aspect here is the new opportunities that arise from this, where we can address long-standing problems with novel methodologies. And in particular, for neural network-driven simulations, we can really make use now of this advantage of having an increased flexibility, adding more data constraints, having a better performance, and we can also apply this potentially to more complex physical models in the future. Thank you for listening.
Hello. So thank you for the talk. It was really interesting. So I had a quick question about the translation of your images. And at what time do you start getting weird features from your images? You input your data and you're getting something out. When do you start getting weird features that might not be real and kind of going into your uncertainty of the model?
Right, yeah, that's a good point, yeah. It's part of the risk factor in there, of course, that basically the model tries to synthesize realistic data, where we usually see the deviations then in the end is when we are basically approaching, when we are imaging features that are not well covered in the individual data sets. Like if we have an unbalanced data set in that sense, it would be kind of an unexpected feature. I think the good part so far that we encountered with this was that when we have artifacts, we can easily spot them. Like if there's an underrepresentation of certain features, we immediately see them. The important aspect of this method as well here, that's because this is always like taken for, especially on this small scale feature enhancement. So it's not meant to be like, to provide actually like the super resolution in that sense that we artificially generate new information out of nowhere, but we are primarily focusing here on this intercalibration aspect. So on the more global scales, basically, where we are more certain that we basically capture the full statistics of the data sets.
Thank you. And great graphics of the logos on your different
Thank you.
catalogs.
Thank you. It's very nice work. If you go to your 15 slide, yeah. So do you have something in the middle? I am interested in that.
That's a perfect question. Yeah. This is like the regime in the middle, right, where we have some amount of data and some of the physics. So this is like, I think, also like a really nice opportunity for future research, where we can basically take incomplete physical models and add additional free parameters, basically. If we have an unknown coefficient, for example, in an equation, we can replace this, and together with the data that we have and the physical equation that we're solving, we can discover basically those unknown coefficients. And this can be very interchangeable. Like the transition here is pretty smooth, I would say. So we can even like, if something is only partially constrained by data and partially by our known physics, we can add basically additional free components where we can actually extract even more information about the underlying system in the end.
So about the former question, if you have a picture with higher resolution, there is an amount of information in this. So you can measure this, maximizing the entropy of the data that you have. So what about taking the low resolution picture and then trying to find the same amount of data in as an information quantity?
I mean, in terms of a validation, basically, for images. We haven't particularly considered that. Mostly we were trying to, it's a good idea. Mostly we tried to use basically the parallel observations that we have and exploit those to better verify and validate the model in that sense, yeah. Maybe in that regard, something that we're working on, since I was saying like we have limited information and especially like getting more information out of the data, something that we're working on right now is basically the using image bursts of high resolution observations to combine them into a single image. So this would basically make use of a larger amount of information and compiles this into a single image in the end. So it's like one track that we're following here.
Thank you.
Thank you.
In the light. This, we start our business meeting, which I don't know if it's business or not. Now you can put the slides that you were putting before. The set that says final slides or something like that. Okay, that. Oh, we can talk. Okay, so I say nothing. Okay. So this is just a summary of our 3 years of this steering committee. So I don't need to tell you what is Division E, but I just want to tell you that we are one of the smallest divisions in IAU, but we just got 80 new members in these last 3 years. So please push for Division E and let's go up with more members. Well, my next slide is showing you the steering committee during these 3 years. I was the president, Toshi was the vice president, Mingeding was the secretary, and Sarah, our past president, who really helped me a lot in running these 3 years. And then we have 6 at-large members and 4 ex officio members who are the presidents of our main 3 commissions and our interdivision commission, which is an interdivision commission since 2021. Okay, this is my laser. Sorry, I was not finding it. So 3 of our at-large members were renewed in this past election because they can stay for 6 years. And then we have also 2 working groups that we share with Division B and C, and these are the chairs, we are the chairs during these 3 years. For the next one, this is a summary of some of the work we have been doing. So during 21 to 24, we coordinated symposia, focus meeting, and other meetings. So in 2022, which was the IAU in Busan, we were coordinating this IAU symposium, a focus meeting, and of course our division E-Days. In 2023, we had this symposium. In 2024, so now, we have 1 focus meeting, IAU Symposium 390, to which you have been attending, and then our division E-Days. For 2025, and we have this also, this symposium, which is not a General Assembly symposium. So finally, in this 3 years, we have 1, 2, 3, 4 symposia, 2 focus meetings, and our division E-Days. Now the next one comes to our PhD awards, and we have very good set of young students. So we got in 2021 10 applications. These are our main winners, so we gave a PhD prize to Subik Bose, and we have 2 honorable mentions. They got their diplomas in Busan. And in 2022, we had 13 PhD prize applications, so they are giving us a lot of job, to tell you. And our PhD prize winner was Shahir Chen, and luckily he could not be here because of a health problem to give his talk. He came, but he got ill. And then we have Chuto Beki, so we listened him, and then Pradeep Kumar Mitra, who could not come. And in 2023, we have 10 applications. Robert Sharolim was the PhD prize winner. Devoyoti Kasamanik was to whom we listened. I thought, oh, Devoyoti, you are there. And then we have an honorable mention for Xin Shu, who couldn't be here. And we got the at-large prize to Abril Asade. So, whoops, there is another one. Where is my last slide? One more? Okay. So after elections, this is the new 2024-2027 steering committee. Toshifumi Shimizu will be the president, Jana Kautsi the vice president. I will become the past president and advisor. Then we have 3 new members. They are Maria Eve Cremades Fernandez from Argentina, Maria Madiarska, she's from Bulgaria, and Paul Kelly from Australia. So these are our 3 new members that add up to our old members, who are Roberto Sederli, Alexander Nindos, and Dargesh Tripati. Our new ex officio members are the new presidents of our 4 commissions. So They were the vice president during the previous 3 years, and now they are ex officio members. And concerning our working groups, our working group on solar eclipses continues being chaired by Song Kwang-kyu, and our working group on coordination of synoptic observations of the sun has a new chair, that is Sabrina Brechet, and a co-chair, Dipankar Banerjee. And having said this, this is just a short summary of all the work we have done during 3 years. And I now invite Divyen, do you want to see some words about Commission 4? Yeah, Commission is E4. Yes, of course, it's E4.
All right, so so I am just taking over Commission A4, which deals with the impact of magnetic variability on solar and stellar environments. So the motivation of this commission, which was put in place, I think about 3 years back in Busan, is to take our understanding from the Sun-Earth system and the solar system and apply it to other worlds beyond the solar system. So we look at the impact of solar and stellar variability more on the long time scales on planetary space environments, atmospheric losses, and habitability. So it's kind of a nice commission which bridges what we know about the Sun-Earth system to other star-planet systems. And I would love if you guys who are interested in this to join the commission. When you're joining as a member of the IAU, you can choose a few commissions to show interest in. And we often host meetings online. We have symposia that we support along with Division E. We had a symposium in Brazil in 2016, and we are planning to host something in 2025. So yeah, please join us.
So, Alexei, do you want to say something about your working group? You can come up here. Divyen, you could have come.
Do you have my slides? Do you have my slides? If I
ask them.
Yeah, me. I do, but it may take some time. Let's see. It's probably down there.
Okay, so I have received this feedback from a lot of people attending this meeting that they would really prefer for people to be physically here, and preference should be given for talks to the people who are physically attending. So I think this is a feedback that should probably go from the division presidents and the commission presidents to the IAU, that we should really give preference to those physical attendees who are present here or in future meetings for talks. This is a feedback that I have been receiving from a lot of people. I don't know what you folks feel about it, but the division business meeting is what, where we discuss such things, and we provide this feedback to the IAU Executive Committee. Okay. You on the mic? Or you have the mic? Okay.
Do you want to come up and talk?
Yeah, let me just talk without slides. I mean, it's okay. It takes too much
They
time.
cannot find the slides.
They cannot find, for some reason. And I
Okay.
cannot find the memory stick anymore.
You have this.
Okay, so then I don't need it. Hold it. All right, so sorry about that, taking too long. So I'm outgoing chair of that working group on coordination of synoptic observation of sun, long name. There are 54 members of that group, so I think it's a kind of large working group from 19 countries. So it's a well international representation. The group is mostly concerned about, again, from the name, coordination of long-term synoptic observations, data preservations, historical data. So the last several years, we were concentrating on four topics. One is the preservation and digitization of records of past solar activity. And it actually includes not only solar, but stellar data. So, for example, we uncovered the old Mount Wilson HNK program data, the real data, not published. So it was a kind of surprise for the stellar community. You may remember that the working group also promoted and IAU, I think it's IAU General Assembly in Studies in Vienna actually passed the resolution about the importance of the preservation of historical data. This year we did a community survey on basically what historical data community feels needed to be preserved. And we just published the results of that survey. So there is a long list of different data sets that somewhere in different countries. Then, so that preservation and this one topic. Then other one is we're working on developing a community kind of coordinated sunspot number time series. So you know that it's not my slides, by the way. You know that sunspot number now in a version 2, but there is a now discussion of version 3. So very soon we will see probably version 3. Some of these discussions happen as part of sunspot number workshops, and the next sunspot number workshop will be this year in Kyoto, Japan, on October 7th to 10. So if somebody is interested, you can still attend that. Then the third topic that we were concentrating is access to modern and historical data. And it's something between, helping to assign DOI numbers, place data in aggregated place, easy to find this kind of things. I have a DOI number for paper that was published that has this information. So if eventually you find this presentation, we'll see it. And then the fourth topic that we concentrate was on a continuation of synoptic programs threatened by budget cuts. So we all have data, observational data from the ground, and some of these observatories are going away, right? So that's the question: how to ensure that there is a continuation of this activity from the funding. Some of this activity is done in collaboration with other groups, and so in my slides, I want to mention that last year, International Space Weather Coordination Forum was assembled by World Meteorological Organization, COSPAR. COSPAR was part of that. This was, despite the name, it was a very small meeting by invitation only, and I was asked to present that working group. And so in my slides, I have this one slide that I was asked to present about this. And I indicated two specific issues that relevant to our working group. One is this kind of global coordinated planning for the worldwide ground-based networks of solar observations. And I mentioned SPRINT network in Europe and NGGWANG in US. And then the second topic I outlined was developing a framework for unrestricted international cooperation. Specifically, I was talking about multi-vantage point observation of the sun, but that unrestricted international cooperation is important because very often we see everybody for collaboration, and then there are restrictions of you cannot work with this, you cannot work with that, this data restricted, all of this. I think it's important.
And so, as a continuation of this activity, this International Space Weather Coordination Forum actually just published the coordinated teams, and two discussions are included in the coordination team. So I think it's very important. So maybe as a concluding remarks that, in my opinion, and the opinion of members of this working group, there is a strong motivation for continuation of this working group, and I have multiple things to support that. And we invite everybody, all astronomers, not only solar, but astronomers at large, who are interested in this long-term synoptic observation, preservation, and historical data, to join the discussion, right? We feel that there are certain aspects that we are not fully explored by this working group, and hopefully the next chair and co-chair will explore that, continue that. Some of these topics that I think are broadening the geographic collaboration. So I'm thinking about, we need more astronomers from African continent, South America, Asia. Then we also need to broaden in collaboration with other groups. And for example, IAU has a global coordination of ground and space astrophysics. This is also working group, right? Even the coordination with a working group on eclipses, I think it's very important. We're looking at some historical data, and early historical data on eclipses, right? Lots of this data are in libraries behind paywall, right? And so how you get this data, right? From 18 whatever photographs, right? I paid like $60 per photograph from some university in California to, for 3 of them, right? My personal money, right? So it shouldn't be that way. It's a scientific data that should be available for, that's the aspect that I can see two working groups can collaborate and develop some, path forward or, way to address that. And then, we are approaching some of our data sets, approaching the maturity level that actually other communities can use. Sunspot number is a perfect example, right? So climate communities using sunspot number, right? Is it this one data set or 100 other sunspot number, time series? I think there is a need for develop the standards for this kind of curation, how you update this standard data set. So, and congratulations to new chair and co-chair.
Well, congratulations. I want to say, so you can join any commission from Division E at any time. And you can also join the working groups by you send an email to the chair, and you can also join the working groups. And this is very much welcome, because these two working groups work very hard. Repeating the word, but the working groups work very hard. And as Alexei said, there is a resolution by IAU in Vienna supporting synoptic observations as historical observations. So IAU considers this, as well as the eclipses, very relevant, okay? So now I invite, Sarah wanted to say something?
Hello? That was a strong. Okay. Sorry. So I just wanted to respond a little bit to Debendu, because this question is actually something which has been coming up IAU-wide, but I wanted to reinforce something that the IAU is really intending at this mission, which is the inclusivity of the hybrid format, because there's a lot of reasons why people don't go in person, and they're including but not limited to health and financial reasons. And to have this be a truly international inclusive union, the movement is in the direction of hybrid in order to make it open to more people and to inspire people around the world. So although I respect your point very much, Divyendu, I think it's important to note that, like we received a message just today from Kevin Govender saying, please make sure that we treat our online participants equally and we look for their inputs, and that, it goes into the spirit of this meeting, so.
So now the working group on solar eclipses and the chair. Thank you.
So actually, we memorized my former chairman, Professor Pasakov, and it's my pleasure to give a talk concerning activities of our working group on solar eclipses. So it contains the two parts. The first one is the scientific progresses from eclipse observations according to the statistics from ADS-ABS. You can find that there's more than 350 papers published during the last 3 years. And almost half of them are referring papers. It means that the eclipse observation is still valuable, vivid, and precious for understanding the sun and solar terrestrial physics into the deep. I would like to introduce our own work. For instance, where we do the spectral panoramimetry of solar upper atmospheres to reveal the complexity of these layers, like this one. And after 100 years, we successfully carried out the spectral panoramimetry of Fraunhofer lines in local upper solar atmosphere. To my memory, about 100 years ago, British astronomers did try it, but I don't think that it was so successful. And we found that the panoramimetric properties of these lines are very complicated. Yeah, and then we identified the presence of neutral mid-patterns in the inner corona. This work has stimulated us to carry out the eclipse observation in the last year in Eastern Timor, and we use these twin telescopes. It contains different filters like this one. One for the continuum and one band contains the two neutral lines. We have these two pictures. It's very hard for you to distinguish from each other. But here we have the subtraction of the two images and we get this image. Very interesting. For instance, the dark part indicated the absorption and the bright part indicated the emission. So we separated the two parts, and then we found that there is one in the solar Fraunhofer corona. So this is our newly funded, like this one. And the second part, of course, we should serve for the public. Yeah, as usual, one of our members, Michael Zetter, he presented this eclipse passes as usual, and we organized the solar eclipse observations twice. The first one is last year in East Timor, like this one. And then we also organized the eclipse observations with amateurs. Okay, yeah. And it's a picture from Michael. Michael, are you here? Are you here? He provided us these pictures. They did leave broadcasting to NASA, CBS, NBC, etc. So actually, it's his 60th birthday, he told me, yeah. And we do the outreach before the eclipse observation. For instance, this year, on April 7th, I gave an outreach speech in planetarium of the University of Texas at Arlington. And this audience before my speech, and here I was given the speech. Actually, we're training some amateur astronomers to guide them to do some scientific observations. At least their observations are scientifically valuable, and we want to realize the science without borders. Yeah. And finally, we organized the eclipse workshop with the University of Texas at Arlington. You can see here. This is a mini workshop. Okay. Okay. Thank you very much. Yeah.
Do you have a question? Okay, you have a question. Sorry,
So, first of all, I would like to ask you the wavelength interval coverage of your observations of the flash spectrum, yes. And second, I would like to ask you how you estimated the systematic error. Yes.
This one?
Yes, you saw a spectrum before.
Spectrum what? This one?
Before?
This
Yes, I saw this, but okay, I wanted to know the wavelength coverage.
Okay, the wavelength range is from 516 nanometer to 535 nanometers in this range. Yeah. It contains the green corner line here. Yeah. Here is the magnesium triplet. This. Yeah.
Thanks. And I don't know if you want to answer the second question, which is a little bit difficult.
Thank you. Yeah.
Sorry, I didn't ask for questions. Any question? Okay, so this ends our business meeting, and I want to welcome Toshi as our new president.
Actually, yeah, I should go there.
You cannot.
Okay, so before closing the business meeting today, actually I'd like to give a few words. Actually, in last 3 years, Christina and the steering committee member had a good job. And actually, as you may know, the Division E is the smallest division in the IAU. And the good thing is I learned the more than 100 members are newly joined. Yeah, that's a good thing. Yeah, 80 is a significant. And I like to, Christina has been leading the steering committee activities very well. And I like to express our thanks to Christina and also the other committee members. Yeah, thank you very much. And I'm becoming next president by following the it's a IAU rule, vice president becomes president in next year. So I like to my best effort as much as possible in next years, and the coordination amongst various activities and also coordination with other divisions are important to enhance our Division E related science activities. So if you have any suggestion, comment to Division E, please send me any message by email. So thank you very much.